I'm sorry for the late. I mean, I thought, I thought it's evening time here, so it'd be easy for you guys, you know.
Okay. No problem, sir. I think almost 45, 50 plus participants have joined already, sir.
Okay, I'm extremely sorry. I mean, I was
No,
really
no,
confused. I mean,
sir,
unless,
no problem at all, sir. If you permit, so we can formally inaugurate the session. So then you can start your lecture.
We
Yes.
can reschedule
yeah,
the next one.
no, it's fine. I'm fine. Whatever you guys, I mean, you are comfortable with that, Okay.
Okay.
All right.
Uh, is it okay, sir? If we shall we proceed,
Yeah,
sir?
I think I'm good. Just a minute.
Yeah, yeah. Perfect, sir.
All
Perfect,
right.
sir.
Mhm.
Right.
All right. You can, yeah, let's start.
Yeah.
Recording in progress.
Shall I start or
No.
Hello,
or
am I
you?
audible, sir?
Yeah.
A very good evening to one and all. It gives me immense pleasure to welcome foreign faculty expert, Professor Prabir K. Kole, Professor and Director of the School of Civil, Environmental and Infrastructure Engineering at the Southern Illinois University, Carbondale, USA. Dr. Binod Kumar Kannaujiya, Director, Dr. B.R. Ambedkar, NIT Jalandhar, Deans and Registrar of the Institute, Professor A.K. Agnihotri, Head of the Department, Dr. H.S. Chore, Dr. Selja Bawa, Dr. K. Senthil, Coordinator of this course, participants from various institutes as well as industries, fellow faculty members, and dear students, for the opening ceremony of this GIAN course on practical approaches to soil improvement and sustainable geotechnical solutions, held from 15th to 19th September 2025 through online mode, organized by Department of Civil Engineering, Dr. B.R. Ambedkar, NIT Jalandhar. With this short welcome, I may request Dr. K. Senthil to introduce the course to you.
Yeah. Thank you, Mr. Vipendra. First of all, I would like to thank Chore sir for giving me opportunity to introduce about this course. This course is designed to provide an in-depth understanding of the importance and necessity of improving ground conditions as well as soil conditions for various construction and maintenance of the transportation infrastructures. To be specific, I would like to highlight the course content such as importance and the need for ground improvement, shallow and deep compaction, soil improvement using stone columns, subsurface investigation methods for infrastructure projects, including laboratory and in situ test methods. Also, the ground improvement using non-traditional stabilizers. In addition to that, the course covers the grouting, different types of grouting, and grouting under difficult conditions. Further, the course will be focused on the use of different types of industrial waste materials in highway embankments, slopes, use of geogrid, rubber grid, reinforcement in embankments. Also, the use of industrial waste in flexible pavement construction. Different types of reinforcements in flexible pavements are focused. With this, I would like to say that I believe the international faculty, Professor Kohli, will cover additional topics to help you gain a deeper understanding of this subject. And thank you all for participating in this course. Thank you.
Thank you, sir. Now I may request Dr. H.S. Chore to give a brief introduction about foreign faculty, Professor Prabir K. Kole.
Thank you, Vipendra, and thank Dr. Senthil for giving me an opportunity to to introduce our foreign faculty uh, for this particular course. Professor Prabir Kumar Kole is a professor in the School of Civil, Environmental and Infrastructure Engineering at the Southern Illinois University, Carbondale, USA. His research has strongly focused on geotechnical and geoenvironmental engineering, as well as modeling in geotechnical engineering. His doctoral research work on characterization, water interaction, and geolitization of class F lagoon ash using various sophisticated instruments such as XRF, XRD, ICP, AAS, FTIR, SAME, IDEX, Blaine apparatus, TGA, and DT analyzer, etc. He has made significant contributions to the understanding and advancement of soil mechanics, foundation engineering, and environmental geotechnology. His research spans over the soft soil stabilization, contaminant transport, and geotechnical properties of the coal ash. His prolific academic career includes over 2 decades of the teaching experience, numerous publications in high-impact journals, and several prestigious awards such as ASC Fellowship and Marquis Lifetime Achievement Award. His innovative work in soil characterization and stabilization has garnered substantial grant funding, enabling groundbreaking research projects that have profound implications for sustainable construction practices. His expertise is recognized globally, evidenced by his extensive record of invited lectures and presentations at international conferences. He has also played an active role in a number of research, testing, and consultancy projects in Illinois and India. He is also serving as the reviewer in a number of reputed national and international journals. With this brief introduction of our foreign expert, now I request Professor Kole to start with his lecture. Thank you.
Sir, sorry to interrupt. Maybe I may request everyone to turn on their camera so that we can take a clips.
Also, I need to share my screen, right?
Yeah, yes. Sir, just a minute, sir. Sorry to interrupt. Maybe for a terms of photos. Is it okay? Can take a screenshot. Okay. Yeah, that's fine. I think yes, sir. Please, you can proceed. You can share your screen.
Yeah, okay. Earlier I used to Zoom, but now we are using Team. So
yeah, this is the Zoom only, sir.
Yeah. Let me see. Can you see now? Can you see the screen?
Yes, sir. It's visible.
All right. So thank you, Dr. Senthil, for the introduction, and also thank you, Dr. Hemant Chore, for this kind introduction. So you was a little bit confusion, I thought leaving time, here. So I was, anyway, we can start. So I also thank again for taking the initiative, Dr. Hemant Chore and Soleja Bawa for this GIAN course. Today, I'm going to talk about what are the courses I'm going to cover in the first class. And then the second class, I'll be talking about also the dynamics and soil compaction and the dynamic compactions. So the first thing is I just want to talk about my university. Here, our university is R1 University. It's the top research university. We are in Southern Illinois. It is almost 5 hours from Chicago and 2 hours from St. Louis. It's the big cities. And then we have 200 plus UG program, 80 plus master programs, 30 plus PhD programs, over $78 billion in research. And also our university is quite old, like 1869. So we have a student from all 50 states in US and over 100 countries. And student to faculty ratio is 11 to 1. So it's very less. We have in Illinois, we have top school like University of Illinois Chicago, University of Illinois Urbana-Champaign. So we have a big top rated top school in Illinois. Also Northwestern University in private university. Our civil engineering program ranked like 98 national, and also the Public Institute 123 in civil engineering. So we have a nice campus. We have even own thermal power plant and also like airport, So without further ado, this is the course outline. So I think the course will be the first lecture. I'm going to talk about what is the importance and need for soil improvement. Then overview of ground improvement techniques. What are the different methods that are available? Mainly the hydraulic, mechanical stabilizations, hydraulic modification, soil stabilization by admixtures, various admixture, and also soil modification by inclusions and confinement. And then lecture 2 is basically the shallow and deep compactions, properties of compacted soil, very basic compaction test and compaction control. Then the deep compactions, dynamic compactions, Viber compactions, all the different methods, the deep compaction method, Viber float technique, intelligent compaction, and also controlled blasting. So until this, I think I should supposed to cover today. And then tomorrow, I think I'll be talking about the subsurface investigation method for infrastructure project, laboratory and in situ test. And then the lecture 5 is ground improvement by drainage. Then the different deordering method, basic consideration for the soft soil, and then how to get rid of the water, basically different by surcharge preloading, vertical drain, sand drain, band drain, or weak drain or PVD, and vertical consolidation. And then also tomorrow we'll be doing some numerical problems on this covered topic. And then the lecture 6 is soil stabilization using cement. So basically you need to understand the basic mechanism, what are the different reaction takes place, type of cement, different type of cement, stabilization reactions. Also soil stabilization using lime, types of lime, stabilization reaction, and also different industrial waste like a fly ash, lime sludge, ground granulated blast furnace slag, and cement clean dust. Lecture 7 also will be doing non-traditional stabilizer, basic geopolymerizations, durability of stabilized soil, thermal modification, and ground freezing. And then the next one, the lecture 8, will be grouting, different types of grouting under difficult conditions, ground anchoring, type of anchoring, soil nailing. So there are a lot of things we'll be covering in one day. So we'll see, you have to go very quickly maybe, And then lecture 9 is organic and peat soil stabilizations. So it's much more challenging. And then also mechanically stabilized, reinforced retaining wall design, different types of geosynthetic material, and how to use geosynthetic for retaining wall design. And the last one, the lecture will be the sustainability and geotechnical engineering, importance of sustainability in pavement engineering, only considering the pavement engineering. So I'll be using different references, like a Hausman book or GIAN's book, Kudolto, Xanthakos Das, and also Hall, Jankovac, and then also a different source. Okay. So first thing is, I just want to talk about why this ground improvement is required or importance. So I mean, the ground improvement or soil improvement is required when the soil is not very good, right? So soil, first you need to know what are the different soil types that are available, problematic soil type. So first one is the highly compressible soft clay soil, okay? And then the swelling or shrinkage soil, then collapsible soil, There are organic soil or peaty soil and frost susceptible soil. Okay, these are the different problematic soil. That's why we need to construct any infrastructure on this type of soil. We need to improve the strength of this type of soil, because sometimes we don't have, with a limited space, we cannot avoid this type of soil. So if you want to construct, so obviously we need to improve the strength first, and then put load on that type of soil. So first one, as I mentioned, is a highly compressible soil, a very weak soil. So obviously, if you apply load on this very highly compressible soil, it's going to have large settlement and deformation with time. And also, highly compressible soil, very low shear strength, obviously, and then it's saturated. Obviously, it's going to do that. I mean, consolidation will take place, and then also it will take time because the permeability is very, very low. So usually silt and clay and alluvium, organic alluvium or wind-blown deposit is highly compressible. So most of the time, when you encounter very soft soil, ideally, if you can do that, replace it, remove and replace. So you remove the bad soil and then replace with good soil. So the problem is in the current site situation. So if you don't get that type of good soil, and sometimes to carry that good soil from different source, it takes a lot of time and then also the cost. So it's not a good option sometimes. Then what you need to do, basically, you need to improve the strength of the soil by using different method. Okay, that's why the soil stabilization is coming into picture. Then these are different methods, as I mentioned. So people are using geosynthetic, people are using particle oil or drain. So most of the time for the consolidation takes place, the permeability is very, very low. So what happens if if you apply load, it takes time to get rid of the water pressure. So in that case, so you need to do something like a accelerated process of consolidation. So basically, either you have to do sand drain or different types of vertical drains, PVD, and other things. Also, sometimes we use like a geofoam or expanded polystyrene. So when the load is, when the soil is very soft, it cannot take more load. So we put a very low load on that type of soils. People are using even foam concrete for any type of structures on that type of highly compressible soil. So then the swelling soil or expansive soil or sinkage soils. So again, these soils are susceptible to volume change with fluctuation of the moisture content. So these are the map in US. So there are several places in US. Also, we have that expansive soil, like in Colorado, Texas, Virginia, and California, and some part in South Dakota, North Dakota. In India, we have, I think the expansive soil covers almost 20% of the land area, and we call it black cotton soil there. And most of these soils are located like in Maharashtra, Madhya Pradesh, MP, Gujarat, Andhra Pradesh, Karnataka, Tamil Nadu, and Rajasthan. And this is obviously, you can find it also arid and semi-arid region of the central and western Deccan Plateau. So then we have another soil is the collapsible soil. So this is like a normally processed porous structures with high void ratio, just like a honeycomb structures. If you apply load, it's going to collapse. So collapsible soils are very low density sill type soils, and usually alluvium or wind blown, and are susceptible to sudden decrease in the decrease in the volume when weighted. Okay. So and then sudden compaction or weighted. So that's the reason we need to be careful while construct on this collapsible soil. And so basically we generally do consolidation test to find out the collapsibility of the soil. So basically what you need to do, you need to do a consolidation test in the dry situation, and although you need the saturated correct, and then later on you just apply the load and you saturate the soil sample and see how much is the void ratio changes. Okay, so we can find out from there the collapsible potential. So you see the collapse percentage is 0 to 1, no problem. If it is, you see 1 to 5 is moderate problem, 5 to 10 is a problem. So, and then if it is more than 20 is a very severe problem. So again, most common in arid and semi-arid regions. So, and then also in southwest US and part of, so I'm going to talk about like because I used to teach here, most of the time I talk about like what this type of soils are available in US. So I added now in India also where this type of soil can be available. So it's like a semi-arid or arid region in part of Gujarat and Deccan Plateau. Then this is also a type of collapsible soil, the loessal soil, and it's wind-blown deposit in sediment. So again, in US, we find it like near the vicinity of Mississippi and Missouri is close to in our state, we have this type of soil. And India, mostly this is Kashmir Valley or in the Gangetic Plain, okay? Then another soil is highly organic soil or peat soil. So most of the construction purpose for any infrastructures, we generally avoid organic content. If it is organic content is maximum allowed 10 to 15%. If it is more than that, you discard. Okay. So it is very soft or wet or very low shear strength. When the organic content is more than 20%, in a soil, if the organic content is more than 20%, it's called organic soil. And if the organic content is more than 75%, we call it peat soil. Okay, this is a very problematic soil because it has like a very high water holding capacity and very low strength. And sometimes the water content may go up to 200%, 300%. So basically, it's not soil. Basically, it's a slurry, and then how to construct on that type of soil is very challenging job. Okay, so in US we have that Michigan area, Minnesota, Florida, and also in Malaysia. I was there for several years. So there are more than 8% of the land area is a peat. So it is very difficult to construct on that type of soil. So that is very challenging work. And then also in India, in Kerala, you can find it in coastal Odisha, Tamil Nadu, and West Bengal, and Sundarban area, and Bihar, and some part in the northern Uttaranchal. And then the frost-susceptible soil, this is not very relevant there, but some part of the, obviously, Kashmir and other area. The effect of frost action on the pavement performance, what is going to happen? So frost action cause different heaving, surface roughness and cracking. And then also it blocked the drainage and reduced in bearing capacity during thaw period. So that's the problem during thawing is more problematic. And so obviously this frost-susceptible soils happen in a particular type of soil range. And we'll talk more detail. The type and uniformity of the subsoil is also important. It depends on, and then the regional climate conditions, depth of the freezing zone. So most of the time, it is up to a certain depth of the soil, the freezing zones it is, and then also obviously it freezes when there is water table is there, right? So availability to water. So and then obviously what happened, one of the effect of the frost action of this pavement, heaving cause and crystallization of ice lenses in voids, and then soil containing obviously the fine particles. Okay? So if it is a granular type of soil, it's not a problem. So it's mostly problem is very fine silt and fine sand. So again, objective and emerging trend of this ground improvement course is basically in a ground improvement method is traditionally aimed to improve the soil or the major function of the ground improvement as a foundation or construction material have been one or more of the following. So basically any ground improvement and program, what you do basically increase the shear strength of the soil or the bearing capacity, and then reduce the erodibility, reduce stress distortion under stress. So if you apply load, it can take more load. Then the reduced compressibility, then the settlement will be less, the control sinkage and swelling. So everything is correlated. And then control permeability. So the water is a culprit, right? So you reduce the permeability, reduce water pressure, and then prevent detrimental physical and chemical changes due to environmental conditions. There is freezing, thawing, or maybe the wetting, drying. Okay? And then reduce susceptibility to liquefaction. So these are the few main objectives for any ground improvement technique. Okay. In broad sense, you can see like for any ground improvement method, we divide into 4 main categories. So first one is the mechanical modification or densification. So in this method, today I'm going to discuss. So basically, we are not adding anything to the soil. So what we are going to do, we will do the compaction, and then with the compaction, basically we are increasing the density of the soil, and then when the density is increased, shear strength is going to increase. The shear strength increase meaning is it can take more load. So and then obviously if the soil is compacted, then the settlement will be less, and then also the permeability, so water ingress to the soil will be less. Okay. So there are different methods of mechanical modification or densification techniques. So one is fiber compactions, one is dynamic compaction, one is the blast densifications. So basically, most of the time we use different compactor or roller. So for that is the zone of compaction is limited, for normal compactions. But when you need to know or when you need to compact at higher depth, so obviously we need to do dynamic compactions or blast densification. These are the things you need to do. Then the second method is hydraulic modification. So hydraulic modification is when the soil is soft. So what you need to do, you need to get rid of the water. How to get rid of the water? So obviously, consolidation is basically the expulsion of water from the soil sample. So obviously, how to get rid of the water from the soil sample quickly, okay? Because most of the time when you apply load on clay type of soil, so it takes more time to get rid of the water because permeability is very, very low. So there are several techniques you can use so that we can increase the rate of consolidation. So there are very common method is the sand drain. Install sand drain, and so that we can increase the rate of consolidation. Most of the time, consolidation happens. The Zagis theory is mostly the vertical drain. It is the water will drain on the vertical directions, but in sand drain or PVD, the water will go on the radial direction also. So it can drain from both sides, and then that's the reason its consolidation is faster. It takes less time. So the vacuum consolidations and also PVD and the surcharge. So these are the basically method on the hydraulic modification. So basically how to get rid of the water from the clay. So again, then the next one is the chemical modification. So how to increase the strength of, again, this soft soil or clay type of soil by using different admixtures, or you call it different stabilizer. Again, there are several methods. One is when you want to improve the strength of the soil for the shallow depth. When you go for deep soil mixing for the deep soil column, so there is a different method. So you can go up to very high depth. And then the grouting method. So we can inject grouting. There are different types of grouting. We inject the different types of grout material to increase the strength of the clay type of soil. And then the last one is, and then also there are different conventional materials. There are non-conventional materials. And the last one is the geopolymer soil separations. A lot of people are these days doing on these geopolymers. So without adding cement or lime, that is the conventional material, cement or lime, people are using like a sodium silicate or sodium hydroxide and some waste material. Either can be fly ash or GGBS or lime clean dust or cement clean dust, and making the soil is stabilized by using that geopolymer soil storage. Then the fourth one is modification by inclusion. So we incorporate something into the soil by using reinforcement. So it may be geosynthetic reinforcement, or it can be steel reinforcement. It can be steel plate or grid, different type of grid. So most of the time, is the geosynthetic material is high density or low density polyethylene type of material. And then, so basically the soil is can take compressive load, but soil cannot take tension. So obviously the geosynthetic material or geogrid material, they can take the tension. Same thing like in concrete. So concrete can take compression, and then that's why we need to add steel so that it can take reinforce the tensile strength. Same thing, same concept. So then there are different methods also, like a fiber replacement. Geosynthetic reinforcement, rigid inclusions. So all these things are basically, we are adding additional thing or reinforcement into the soil just to improve the strength of the soil. So these are the four main categories from the houseman, but these days, a lot of people are doing some extra things. So like include injecting bacteria to improve the strength of the soil, just like it form calcite precipitation, and called the MICP technique. A lot of people are doing research on that area, but it takes time. But a lot of people for the last 20 years, people are doing in that area also. And then others I mentioned, like a removal and replacement. So it's an easy method. So sometimes it's possible. Sometimes, just for example, we have a soil, very soft soil of, if it is 1 feet, you can remove it and then you replace with good material, gravel or sand. But if it is like think of like a 20 feet, 30 feet, so that is not possible, to remove and replace. So what you need to do, basically, you need to improve the strength of the soil on the top part of the soil. So because when you apply a load, so you know that the load is applied, and then we have the pressure bulb, correct? So if you put a foundation, how much portion of the load soil is heavily stressed, okay? So you need to improve from the pressure bulbs, how much portion of the depth of the soil should be need to be improved. So you can improve that much, and that's all. So basically, when you improve that portion, and then you are good. So, and then there are other methods like thermal methods, or also people are using ground freezing method also. So basically, when you freeze the whole ground and then you do your construct. So I know I was involved with ASE geotech tools. So we developed a ground improvement technique. So that is a good source of material. You can find out ASE geotech tools. So there you can find out all the different technique, all these different methods or techniques, like a lot of pictures, case studies, fact sheets, all these things you can find out from there. And then also last one is the electrical. So basically when the soil is very clear type of soil, so we need to do what you do. You need to put some current between the soil, at anode and cathode, and then obviously there will be H2O will be divided by H plus and H minus. One will go to anode and it will be cathode, and then you can consolidate the soil sample quickly, basically get rid of the water from the clay. Okay, by using this is called the electroosmotic method. So this is I just prepared this one for the soil stabilization method, but all these different methods I put it in one. So most of the time we use the mechanical, chemical, as I mentioned, so mechanical, chemical, hydraulic, and inclusion or reinforcement. I added that here biogeotechnique. And then also the mechanical, as I mentioned, we are not adding anything extra to the soil. So using just different compaction or blast densifications, so we can increase the density of the soil, and ideally, eventually it will increase the shear strength and it can take more load. So the compaction, it can be shallow compaction, so using different type of roller. So we will talk about that. And then also the deep compactions. So then it's the dynamic compaction, and then also you can use dense blast densification. The chemical stabilizations we mentioned just now, the traditional admixtures, the calcium based, mostly the cement, lime, and fly ash. So most of the time it is forming either calcium silicate hydrate or calcium aluminate hydrate or a tringite. So we'll talk more details about that. That is responsible for the strength gain of the clay when you add these chemicals. And then non-traditional admixtures, we can use silica fume, we can use cement clean dust, we can use lime clean dust, we can use GGBS, we can use different types of polymers that can be organic polymer or inorganic polymers. It can be ionic, anionic polymer, different types of polymer can be used. So this is like a non-traditional admixtures. For hydraulic modification, I already mentioned, this is drainage. So if it is granular type of soil, so what you need to do, you just make a well, construct a well, so all the water will come to the into the well from the surrounding area, and they just pump the water out. So basically, whatever the water table was there initially, it will go down. Basically, it will be forming a inverted cone of arch, and there is obviously some influence, radius of influence. So while you're designing your the wells, obviously you need to know how many well you need to install, what type of pump you need to use, what specification. There are different square or triangular. So all these things we need to know. So that is basically the drainage. So if it is a granular type of soil, you can use like a well method. If the soil is clay, if you make a well, obviously the permeability is so low, water cannot come to the well. So then what you need to do, either you need to do sand drain or PVD or geosynthetic drain. Sometimes geosynthetic sand drain, also geosynthetic is encased into the sand drain. So these are the different techniques. Basically, this is hydraulic modification. And then reinforcement by inclusion and confinement. So obviously you have to do the anchoring, you have to do the reinforcement, also the anchoring. So the reinforcement, as I mentioned earlier, like you can insert the metal strip. So basically the idea is it can take the tensile load. Metal strip, it can be geosynthetic material, it can be geogrid or high density, mostly high density and lower density polyethylene type of material. It can be fiberglass, it can be bamboo strip, all these different types of materials. Sometimes it can be used for this type of material used for temporary, or sometimes it used for permanent. Then the anchoring, we can use most of the time is the metal, the soil nail, and then also the ground anchor. Okay, and then the biogeotechnique. Here, there are three different techniques. So one is biocementation, bioclogging, and biogas desaturation. Most of the time, inject some bacteria, and obviously you need to supply some food for the survival of this bacteria, urea and other food source. And then the bacteria will form like a calcite precipitation, precipitation. And then the soil will be stabilized. So this is called the MICP technique. So as I mentioned now, the ground modification, there's a four main methods. So, as per the Houseman, 1994. But again, as I mentioned, people are using geopolymer, people are using biogeotechnique. So these are the four main methods: mechanical, hydraulic, chemical, and modification by inclusion or reinforcement. And then also thermal modification and the ground freezing things is not very common, but people are using this for the thermal modifications by heating. So obviously it evaporates water and cause permanent changes in the clay minerals. Again, we need to understand that what is happening inside the clay. Okay, so and then also the soil stabilization by freezing. So basically, this solidifies the all part of the water. So basically, when we have a clay in the voids, all the pores are pore water is going to freeze. So basically, it holds all the soil particles together. Okay, so so that is by freezing method. Okay. So first thing is, now I'll just go leave you of that all these four methods. So mechanical modifications. So mechanical, as I mentioned earlier, also like we are not adding anything extra into the soil or clay. Okay? So just to increase the soil density. Okay. So how we are going to increase the soil density by using different method, compacting method, compaction. So application of this is the short-term external mechanical force, including compaction of the surface layer by static load, static compaction. It can be vibratory, or it can be impact roller or plate vibrator. So different types of compaction, you can do that. And then also, as I mentioned, this is limited to a certain depth. So, and then if you want to know the compact at higher depth, so then you have to do the deep compaction by heavy tamping. So there is we call it sometimes the deep dynamic compactions at the surface, and then the vibration at depth. Okay. Then I already mentioned the ground improvement by modification, by hydraulic modification. So basically, we are that removing the pore water pressure in forced out of the soil via drains or wells. Okay, so that you are increasing the rate of consolidation, quickly. So if it is a coarse grained soil, this is achieved by lowering or groundwater table through pumping from boreholes or trenches. There are several methods. We'll talk about that. And then also the fine grained soil. So basically, what you need to do, you need to put some external load. So when you don't need the construction need to be quick, so what you need to do? So basically, you put a heap of soil on the top of that, the construction site, and then leave it for a long time. So what is going to happen? So obviously, because of this load, the pore water pressure is going to release, and then with longer times, so all the pore pressure will gone, and then basically, meaning that the consolidation already occurred, and then you could release that the surcharge load, and then do your actual consolidation, actual construction. So idea of doing this preloading is basically whatever the settlement is going to occur in a particular site, it is already occurred. So then you put an actual structure, it's not going to settle much. Okay. So, but the thing is, obviously, we need to, when you do that, so how much time you need? Sometimes because of permeability, you need to keep it for 4 or 5 months or 6 months. And then obviously, how do you know that, when you to release that the pre-consolidation load? So what you need to do, you need to put a settlement plate before that, and then you need to see how much is the settlement. So with time, when the settlement is almost constant, so meaning all the settlement is already occurred, or you need to install the pore pressure transducer into the soil so that so when you see there is no pore water pressure into the soil, so meaning all the water gone out, so meaning the consolidation is over, then you really remove the preloading load. Okay. And then also there's another method is, as I mentioned, the electrical forces or electrokinetic stabilization. So basically, you put it to pass the electricity, and then anode and cathode, and then with the voltage difference, same thing, same concept like hydraulic conductivity, correct? So the water will move from higher level to lower level. So, and then there should be head difference, correct? And the distance, we know that is hydraulic gradient. And the similar concept here is the voltage difference if we put, and then one is anode and cathode. So water will be just one will go to anode and cathode, and you can take out the water from there. Okay. The chemical method will go, this is, we are changing. So basically adding something, chemicals or some stabilizer into the soil. And then the surface layer or column of the soil at certain depth. So obviously we can do, there are different types. We have a shallow stabilization technique. We have a deep stabilization technique. Sometimes, depending on situations, we can get deep stabilization. Most of the time, we just do a stabilized column, and then you put your structures on top of that. And then sometimes the soil is so soft. So what you need to do, first you need to do shallow stabilizations, and then so that you can bring heavy equipment over there, and then do the boring and stuff for, and then other mixer, so that you can do for deep column or deep mixing or deep mixing or at very high depth. Okay. So and then addition. So this addition includes the natural soil, industrial byproduct, or waste material. Most of the time people use. That's why the sustainability is coming into picture. You need to use different types of, for any soil stabilization, if you use that different types of industrial byproduct, so that you are not dumping that industrial waste to the landfill. You are using it for improving the strength of the soil, and then basically that is much more sustainable. But only thing is, sometimes some of the waste has a lot of toxic heavy metals. So what you need to do, basically, after stabilizing, you need to do or conduct the leaching test and check whether how much the concentration of the leaching material, the heavy metal concentration is coming out from the stabilized soils. So that is very important. Otherwise, the leachate will contaminate not only the soil, and it will contaminate the groundwater. So we don't want that. So that's the only thing you need to do, obviously. And then when additives are injected or by a borehole under pressure into the voids within the ground or between it and structure, so it's called the grouting. So there are different methods of grouting. We'll talk about that. So basically, it can be permeation, it can be jet, it can be pressurized. So there are several types of grouting materials and methods to improve the strength of the soil. And the last one, as I mentioned, is a modification by inclusions or confinements. So you can use any type of material. You can use fibers. It can be polypropylene fibers, or it can be steel fibers. It can be metal strips. It can be metal bar. It can be meshes, or it can be the different types of fabric. So geosynthetic material or geotextiles materials. And then also, as I mentioned, it can be in situ reinforced. Reinforcement can be achieved by either soils or soil nails or the anchors. Okay, and then also you can use design a retaining wall, earth retaining structures by using this type of material, like an inclusion. So either MSE wall, either metal strip, or maybe geosynthetic type of material. Okay. So as I mentioned, so for any improvement method or technique, so it is not necessarily that you need to use only one method. You can use one or more possible method to improve the strength of a particular site. Okay? So there are a lot of things you need to consider for how to improve what method you need to use for a particular site to improve the strength of the soil. So it is in its broadest sense, any interference of the natural state of soil and the rock could be termed, obviously, ground modifications. And then we need to check the suitability, we need to check the feasibility and the desirability. So what strength you need. Okay? So few things we need to check. And the choice of method depends on, there are several factors. Types and degree of improvement you need, how much strength you need to improve a particular site, what type of soil or geological structures or seeping conditions. Again, most of the time, as a geotechnical engineer, so we deal with two types of soils. So one is called the fine grained soil and coarse grained soil, correct? So coarse grained soil is better, and most of the time we call it gravel. And as per unified soil classification system, gravel and sand. And there are different, again, sand also, fine, coarse, and medium. But again, for fine-grained soils, the silt and clay, right? So there are different classification systems, but again, mostly the problematic is the clay. If there is a clay is there, it is a problematic. So sometimes, and again, we need to know different clay minerals. Okay, so whatever you studied in soil mechanics, like that we need to know what type of clay minerals are there. Clay is less than 2 micron or 0.002 millimeter, but there are different types of minerals. So it can be kaolinite, it can be montmorillonite, it can be bentonite, it can be illite. So all these different minerals, how the what type of bond there, and depending on that, it can be expansive or swelling, and then it can be van der Waals, it can be hydrogen bond, it can be strong electrostatic pressure. And then also you need to know the clay is negatively charged particles. So that's the more problematic. So again, the soil type is very important. Seepage condition is very important. And then also the cost, the size of the project may be decisive. Sometimes, the big project, generally, you need to, people use the soil stabilization technique. There are several methods, as I mentioned, so you need to be careful which method you are using. And then also the availability of the equipment and the material and the quality of work. Sometimes you need to use, just for example, PVD or any stone column or any other. So what do you do? The material should be, the instrument should be available. So otherwise, if you transport from a long distance, and also sometimes most of the time is economical if you use locally available material. So that is important for any ground improvement or ground modification techniques. Okay. So again, as I mentioned, this is one of the methods I just mentioned. The factors that affect the selection of the ground improvement method. The soil type is most important. What type of soil? The cost of the entire project, availability of the equipment, presence of other structures. Sometimes, so just as I mentioned, so maybe you are using the dynamic compaction. So what happens if you use dynamic compaction? If there is a structures nearby, the vibration may create damage to the structure. So we need to be careful what type of structures there. Okay. The project requirements, environmental factors you need to check, degree of improvement needed. So again, I'm just giving one example, like you are constructing a pavement, and there are different types of pavement, right? So one is the rural road, or maybe highway, national highway, or state highway over here. So depending on that, the requirement, how much the maximum permissible settlement is required, depending on that, we need to, do the improvement. So, degree of improvement needed for a particular project. So that's the one we need to check. And the groundwater table. So groundwater table is very important, where the location of the groundwater tables, because if the soil is saturated, when there is a rainfall, the groundwater table is high, is totally waterlogged area. Sometimes we need to do the construction is in dry situation, then we need to do the different dewatering technique so that the water table can be reduced, and then do the construction in dry situation. Then also materials availability, construction improvement time. Also, just for example, if you're using any stabilizer, sometimes for the chemical reaction takes place, it takes time. So you need to give some curing time for at least 3 to 5 days or 7 days minimum. So these days there are a lot of stabilizer or quick setting time cements. Quick setting cements are available. Different types of calcium sulfaluminate cements or other cements are there. It can do reactions very quickly. And then different types of polymers are there. So we need to know the construction improvement time, how much time you have. Depending on that, we can use different type of stabilizer. Sometimes, if you use different industrial waste, like a fly ash or GGBS, it takes time because it's pozzolanic if you use river lime. So it takes more time, but at the end, and the strength will be quite high, almost close to, lime or cement, So again, but if you want the strength quickly, so obviously you cannot just do that. You cannot use it. And then also durability of the material. So this is very important for any, mostly the chemical salt stabilizations. We need to do the durability test. Okay. So you do the stabilization with the extreme climate these days. People are talking about sustainability and stuff. So, and then climate change. So what is going to happen to the flooding event or, freezing and thawing? So what is going to happen? So you need to do the test for extreme event, wetting, drying, and freezing, thawing, and then you know what is the durability of the material. So because when you construct any pavement, so we don't know what is going to happen. So that's the reason we need to do the durability of the material. Sometimes also durability of the material, if you want to use that geosynthetic or geogrid type of material, so that also degrade with UV light. So people are studying the long-term behavior of this type of material. What is going to happen with UV light? Okay, well, it's going to take a long time, but people are doing that studies. Noise and vibrating during construction. Again, even simple pile foundation. For deep not salt stabilizations, like a deep foundations, or maybe, as I mentioned, deep compaction. So is the noise is a problem. So we need to be careful. And then also how to do that isolation of this knowledge, the CRF velocities. So we need to do some, make a trench and other things. We'll be going to discuss that also. And the reliability of the method, that is also very important. And then also we need to know the performance measurement. So again, any improvement when you do, and then you need to check whether you achieve that the required strength. Okay, so then you need to do some test and then verify. Okay, that this method or of improvement, it really works. Okay? So these are the different things, as I mentioned, for basically all these different methods. Okay, and then so anyone, can I just stop for a minute, and then anyone has any questions or anything? This online things, I know this COVID time we started this, but sometimes it's like a one way. It's not much interaction between this the teacher and the student. So anyone, do you think that I should continue, or just anyone has any question?
Yes, if any participant have any questions, please.
Question. Okay.
Sir, am I audible? Hello.
Hello.
Sir, am I audible?
Yeah.
Yes, sir. Sir, this is Dr. Shashank. Actually, in one of the slides for the fine-grained soils, when you were mentioning the hydraulic modification, in that case, you mentioned that there are, apart from preloading, which is very much popular, the electrical forces can also be used. Sir,
Yes.
so in due course, will we be understanding more about that electrical forces, how we can go for hydraulic modification using that?
Yes. We'll talk about that more detail. Okay. We'll talk about that. So basically, most of the time in this hydraulic modifications, so generally we do like a sand drain, right? So there are vertical drain, one is sand drain. So we just make in the clay, we just make a sand column, and then what you do and apply load, such as on the top there is the sand layer also, so that on the clay the water will go in the radial directions. Most of the time in the there's again one dimension consolidation theory again. For the clay, the water can go only in the vertical direction, right? Correct. So mostly when you see even in consolidation test, right? In the consolidation test, the sample is there in the mold, and then there is a clay sample, and then the porous stone on the top and bottom, and then the filter paper and apply the load, right? So water has, because the lateral sample is laterally confined, so we call it K0 consolidation, water can move only in the vertical direction, correct? So this is one way. And in real life, the consolidation may happen in horizontal directions also, correct? So that's the reason here, if you put a sand column, obviously the water can go in the radial as well as vertical. So that is the accelerated method. So, and then also the PVD. So we will talk more about that. And then also the electrical one. There's 2-3 different methods to how to get rid of the water. So again, so this is for any ground improvement or any soil improvement techniques. The first thing is we need to understand the soil, correct? So again, you need to go back and whatever you studied in soil mechanics, we need to just what type of clay is there, whether it's normally concentrated clay or the pre-concentration clay, all these things. Again, the settlement calculations we need to know, and then also only thing is here the radial things are coming into picture, and then so basically you are increasing by this radial drainage, you are increasing the rate of consolidation faster. That's all.
Okay. Thank you, sir. Sir, actually, that I wanted to know about that electrical forces, actually.
So basically, so what is, there are different volts, so most of the cases, so what is permeability? Permeability is how much the water is going through the soil, correct? So depending on the soil type, so if it is a sandy type soil, so water can go quickly, permeability is higher, right? So if it's a clay, permeability is low because it takes more time. So obviously the water will be flowing because there should be some hydraulic gradient, right? So if there's a head difference, then obviously how much is the head loss? How much is the difference in head? Because of head difference at certain distance, that's the reason this water will flow, and the water will flow when the head is equal. The same thing for this hydraulic, for this electrical one. So we need to have a voltage difference. Okay. So if there is a voltage difference, then the water will also flow. Okay.
Okay, sir.
So and there is a gradient. So that is called the electrokinetic gradient. So it's a different gradient, but it's a voltage difference. Because of the voltage difference, water will flow. So the other one is the because of head difference. This is the voltage difference. Same thing for the heat flow. Also, there should be a temperature gradient, right? So the heat difference, then the heat will flow, correct? Same thing.
Okay, sir. Thank you so much, sir.
Any other questions till now? So basically, I explained all these 4 methods, and then also these days people are using that the check table I mentioned. So over here, it is not published yet. So I'm going to write a book chapter, and there I propose this, and we need to add some. We are still modifying this. So basically, as for the Huseman, so basically the biogeotech, it is not there. So only these 4. Obviously, for the last 20 years, people are using this biogeotechnique. So we added that. Any other questions?
Yeah, one question from my side, sir. I'm Sadanand Govilkar from the industry. You mentioned in your presentation about use of fly ash and GGBS. So I just wanted to know whether the specifications are same which is used for concrete about the fly ash and GGBS, and second, how we can use that. What size of quantum? That was my first question. And second is, by any cases, where CDW is used for soil stabilization?
Can you repeat the second question you mentioned?
Are there any cases about use of construction and demolition waste for soil stabilization purpose?
Oh, okay. Thank you for the question. So basically, for obviously for the fly ash things, so there are, again, we need to know what are the different types of fly ash. There are different types of fly ash, correct? So depending on how the fly ash is produced. Okay, so fly ash is produced from this, from the thermal power plant most of the time, but people are using, again, from the coal-based, coal-fired thermal power plant. So basically, it depends on degree of pulverizations, type of coal used, and how much is the furnace temperature, a lot of things, and then how we are going to dispose. That depends on based on that, it can be fly ash, it can be bottom ash, it can be lagoon ash, all these different types of ash, correct? And then most of the time, for fly ash, there are two types. One is class A fly ash, another one is the class C fly ash, right? So class F is pozzolanic. We need to add obviously more little bit of lime or anything so that it can activate and it can. If I'm just talking about if you want to stabilize its soil, so you need to add that. And then obviously that again ASTM C618 the major oxide you need to see the silica, alumina, and iron is it should be more than 70% and calcium is less than 5%. And then also you need to check the loss on ignition, how much is the unburned carbon present in that fly ash. So that is fly ash, class A. Again, class C is better because it has more calcium. So I know that Beverly lignite fly ash, the coal, if you burn that, obviously you will get that. So basically, so depending on the type of fly ash, it depends how much calcium is there. So the calcium is the one that will react with the soil. So the soil is basically, again, you need to go back what type of soil is there, correct? The soil is basically what? The silica and alumina, correct? Silica, alumina, iron, all these different minerals.
Yeah.
And then it is reacting with the fly ash, and ultimately it will be forming calcium silicate hydrate or calcium aluminate hydrate. These are the two things it's going to form, and then that's why it's responsible for the strength gain. So in terms of GGBS, so GGBS is obviously is a byproduct of iron industry. So depending on, it is a coarse material. Sometimes what do? You need to grind it. So just if you grind it, increase the surface area, so much more reactive, and then you can use it, So, and then also sometimes when you use that fly ash class, if you're using class F or GGBS, you need to add some activator, either lime or a little bit of cement into that so that it is much more reactive. Again, as you mentioned in the field applications, so obviously, for any practical applications, so what do you do? Take out the soil sample from the site and lab test you do, and you have to do different trial and error methods, and then find out how much is which one is the optimum percentage for that particular. But the second question, as you mentioned, the fine, people are using the construction demolition fines also for the soil stabilizations, sometimes the rock fines or others. Again, most of the time it is, if it is a construction demolition waste, sometimes demolition waste also, the concrete, sometimes there are unreactive cements are there. So people are using that for soil stabilization. Again, you need to do few tests, and then only you will know how much is the strength required and for a particular purpose. So that is one. I mean, I know that I did research on that area, a little bit of recycle aggregate and mixing with although I'm geotech, but I did on concrete. And you have noticed that recycle aggregate and with a little bit of fines is better, even up to 40%, 35 to 40% for freeze-thaw durability. Even.
Yeah. Thank you. Thank you very much.
Does it make sense?
Yeah. Thanks.
Okay. And again, for any soil stabilizations technique or method, so most of the time, what you do is we need to do a little bit of chemistry. I mean, if you're using limes, obviously you need to know what type of lime you're using. Okay. And then also you need to mix with soil and then see the pH. If the pH is around 12, so it is good. And then you need to, again, what type of method you are using. So lime is basically 8 to 10%, maximum 9%, 10%. If you add more lime, the strength will go down. And also, if you're using cement, obviously, if you use cement, obviously the strength will go up. But at the same time, the cost will go up also. But that's the reason we use different types of waste material. A little bit of fly ash, a little bit of lime, a little bit of cements in the combinations, and they do trial, and then even it will give more strength. Okay. Any other questions?
I think, sir, there is no more questions.
Okay. So, all right. So I think then I have to share the different screen now.
So, sir, shall we take 15 minutes break or we can continue?
Okay. Yeah, I am actually, it's totally different thing. I mean, I thought it'll be in evening time class.
Yes, sir.
Yeah, okay. Yeah, let me find out my slides and stuff. Okay. Yeah, 15 minutes. So what time will be joining then? I know it is already
That
delayed.
8 o'clock. 8 o'clock would be fine, sir. So that
After
will.
10, after 10 minutes.
After 10
Yes.
minutes? Okay.
Yes, sir.
Okay, sir.
Right. Thank you so much. Hello.
Hello, sir. Am I audible?
Yeah.
Yes, sir. So, sir, we can start the second session.
Okay. All right. So can you just tell me, like, after, 15, okay. This is 1 hour, 15 minutes, correct?
Yes, sir.
Okay. All right. Sorry for the confusion again. So,
Yes, sir. Due to time zone, sir.
yeah, anyway, I thought it'd be easier for you guys in the morning, but anyway. So, again, welcome back. I mentioned this in the last slide. So these are the 4 methods we already explained, that mechanical, hydraulic, chemical, and this modification by inclusions, and all these different methods you mentioned. So others here, you mentioned that the removal and replacement and the thermal or electrical. So I'm just going to go mostly now this mechanical modification part. And then also basic compaction method, and then also the dynamic compaction and blast densification. The first thing is I'll cover only the mechanical densification part now. As I mentioned, removal and replacement. So these are the different things people use. Removal as this easy way to remove and replace, but sometimes, as I mentioned, it's not feasible. And in situ ground improvement, we mentioned that there are several other methods: pre-compression, vertical draining, in situ grouting, stabilization reinforcements. Okay, so what is replacement and removal? So these are the things. Is the oldest method to remove. Simply remove the bad soil and replace it with good material. Okay? So you have to be careful sometimes. So when you are using this, is a clay you replace with gravel, but sometimes if the gravel is mixed with clay, its behavior is like a clay, so it's just useless. And that's why people are using geotextiles or geogrid into that, so that it's a separation between these two materials. Okay. And so and then what happened? The soil will have to include contaminated soil and organic soils, or also method is usually practiced only above the groundwater table. So obviously the replacement, you can use it when the soil is above the groundwater table, above the groundwater. So if it is a wet soil, you cannot use this method, replacement removal. So you see the original figure in this figure: original strong soil, original soil, and loose soil. So what did you do basically? Soil excavated. So basically, again, the compaction process, correct? Excavated, add some water, and then compact in layers. So that's why is a cell water content adjusted and adjusted in layer. So basically, that's why you call the engineered soil, correct? So engineered soil, real soil, we don't know what type of soil is there. what is the void ratio, what is the porosity and other things. So here we know how much is the density, how much is the water content, everything, and then you know how much it can the soil can load the soil load, it can take the load. Then the partially replaced soils, instead of whole soil, you just layer of material, new material we added, and compact the soil, existing soil. So there is one partially replaced soil. This is the figure D at the corner here, the new soil. So you just put all new material in different and compact it in layer wise. Okay. Then modified with soil additives. So again, you can use different additives and then compact it and then do this. Okay, do this in layers. And then also the reinforcement soil, obviously, you know, you can do this and put reinforcement layer and then compact it and then put another reinforcement layer like this, or using geocell. So this is basically the removal or excavation of the replacement. So excavating the poor soil and replacing with having desired properties is normally economical. So obviously there are every method some advantage and disadvantage. When the soil is, so it can treat it up to 3 meters. So you cannot do more than that. And the water table is below 3 meters, obviously. You know, it should be in dry conditions. So what are the different 4 steps over here? Excavate the soil, modify it, place it with modified soil by replacing a thin layer. So you have to put it in a thin layer. So that's why the compaction, you know, when you do put it in 3 layers, in standard Proctor, UNIC, or when you use the roller compactor, so you need to put it in 3 layers. And then also compact each layer with rollers. We'll talk more details. And then 4 process of modifications. First thing is alter the water content. You change the water content. Then the V is basically the replace, soil replace, and then the mix with additives, and then include or reinforce. And as I mentioned, this is removal and replacement is easiest and oldest method. So another method, in addition to the 4 process over here, there is also thermal process. As I mentioned, it can be thermal, it can be freezing. Okay, so thermal process is rarely adopted, you know, expensive and skill involved. So when the suitable you are eating heat, right? So it's suitable for wet and organic soil and heat up to 500 degrees Celsius to remove the organic matter and use modified material. So there, again, this is a different thing, and we'll talk more detail or organic or peat soil in that in thermal process. So some of the method situations in this found in this effective are economical. So again, replacing with poor compaction of excavated soil, adjusting with the moisture content, and then increase the bearing capacity. Replacing with a layer of sand, intercepted. So obviously sometimes the clay layers, you put a layer of sand and then put clay again and put layer of sand. So basically you're putting sand sandwiched between this clay layer. And then when you apply a load, so basically the water can go easily, you know, in that clay layer. So because the sand permeability is higher, so that can basically settle quickly, and that is the soil properties will be better. Replace with the new soil using when good quality of soil is available, very nearby sites. So that is again availability of the material. You mentioned the different points. Replacing the soil with cement as an additive is useful when good quality soil is not available. So in that case, you need to use some the cement. Again, people are these days talking about sustainability. You know, ordinary Portland cements. Even the production of this itself, it generates a lot of CO2 and, you know, greenhouse gas. But again, when there is no choice, you know, we have to use it. Okay. And then idea is basically increase the strength of the subgrade for the road subbase. And then also replacing the soil with lime, reduce the sinkage and swelling behavior of high plastic clay. Again, what type of soil you're talking about. So we need to use that different type of soil. So and then what type of stabilizer you're using. So again, replacing the soil with bentonite as an additive is useful in constructing impermeable. So suppose if you're using something impermeable barrier, so you can use a landfill liner design. So in that case, we need to use that impermeable layer. So use bentonite or bentonite, mostly bentonite. Replacing with good soil layer of geogrid, useful for the reduced differential settlement at the base or large diameter storage tank or base of the environment. So you can use that also for geogrid. And replacing with excavated soil thermally treated useful when this PD soil, so it's highly organic and too much of water. So in that case, thermal modification is useful. So then now I'm just going to talk about like the mechanical compaction. So mechanical method. So basically how to increase the density of the soil without adding anything, just like normal compaction. So this is basically, you know already compaction. The compaction is basically expulsion of air from the soil sample. There's a difference between a compaction and consolidation. Consolidation is expulsion of water from the soil sample. This is expulsion of air from the soil sample. So many earth type, any construction such as dam, retaining wall, highway, airport require man-made place soils or engineered soil or field. So when you are constructing from scratch, so we know what density we need. We know how much the load it can take. So everything is predetermined. Okay. So here the compaction is to the compacted soil, that is to replace the density. So basically, what you do, basically the compaction, so we increase the density of the soil. Okay? Increase the density of the soil. Density of the soil is more, meaning it take more load, and then obviously the shear strength is going to increase, the settlement will be less. So densest is achieved through reduction of air voids in the soil. So that is the definition of consolidation, with little or no reduction in the air content. Okay. So what do you need to do in consolidation? Again, already, I'm just telling it again. So it's very fundamental things. What happened, for when you do compaction test, so compact the soil, meaning if you add water and density is increased, add a little bit more water, density is increased. So, and then it will reach a maximum value, that is the optimum moisture content or water content, that density will be the maximum. And then if we add more water, obviously the density is going to decrease. Okay? So the standard Proctor graph. So basically what you need to know, so what is happening basically in consolidation. So soil particles, we add water, so all the water is coating with that the soil particles. Okay, and then when you add some mechanical energy, just using hammer, so basically they are sliding each other, and then they adjust themselves, and then making it closer, the density is increased. Okay, so that's why the density is increased. So with after optimum moisture content, what is going to happen? So basically there density is increased, so when you add more water, so the water particle is replaced with the soil particle. So obviously the unit weight of water is less than the unit of the soil, so obviously the density is going to decrease. The process, again, this is the difference between this process must not be confused with consolidation, in which the water is squeezed out under the action of continuous static load. So obviously the consolidation is different, so we have the expulsion of water from the soil sample. So that's why, that is theory of consolidation. So when you do the consolidation test, it's a bit different. So first you saturate the soil sample, and then you get rid of the water, right? So it's a bit funny. You want to get rid of the water, but first you add this water to make it saturated, and then you apply load to get rid of the water. So as I mentioned, the compaction is the shallow compactions. We will know what is the theory of compaction. So again, everyone knows this, but I'm just going to go through again. Properties of the structures of compacted fine-grained soil. So what is going to happen? Again, you need to the fine-grained soil. You need to know there are two types. For the silt and clay, mostly the fine-grained soil. These are the two fine-grained soil, and they are the structures. For the coarse-grained soil, the structures are single-grained or maybe honeycomb. Single-grained, again, it can be like a granular type of soil particles. And then it can be honeycomb for, it can be loose, it can be dense. For clay, it's a platy structures. And when you compact it, mostly, depending on the fabric arrangement. So again, it can be flocculated or dispersed, depending on the compaction state. So most of the time is a dry side of the optimum. It is more flocculated edge to face, more strength. And then when it is wet side of the optimum, so mostly it is the parallel, So that's why we need to know the structures of the compacted fine grain. Field compaction equipments. What are the different field equipments generally used to increase the density of the soil? And then field compaction control. So how you know that the density is achieved at the field. So we need to go to the site and do the in situ test. There are several field tests you need to do, and then and then estimating performance of compacted soil. So now when you compact the soil, so now you need to know the field compaction. So now how much is what is the performance of this compacted soil? So again, general compaction methods. So we have, as I mentioned, the coarse grain and fine grain. So when you talk about coarse grain, as per USCS, we'll talk about gravel and sand, and fine grain I'm referring silt and clay. Okay. So there are lab tests and field tests. In the laboratory for the coarse grain, granular type of soil, they use the vibratory hammer. So we don't compact it for the sand. So when you compact with the hammer, so that will will splash out. So we don't want that. So most of the time, the coarse grain, we use vibration. For fine grain, we use the falling weight or hammer or kneading compactor or static load and press. This is generally used for the laboratory. In the field, the same thing. We have to use the hand-operated vibration plate, motorized rubber vibration plates. We will talk more detail. And then also in field, for the fine grain, we have hand-operated tampers or seafood rollers or rubber tire rollers for the clay type of soil. So then what is the advantage of compaction? Again, idea is repeatedly I'm telling the increasing the strength of the soil, shear strength. Again, the shear strength is the parameters, that tau is equal to C plus sigma tan phi is the cohesion and angle of internal friction of the material. So most of the time, for the coarse grain soil, the shear strength is coming from this friction. How much is the angle of internal friction of the material? More friction means more strength. And then also for the clay type of soil, more stickiness or cohesion. There is an intrinsic cohesion. There are different type of cohesion is there. And then the decrease for future settlement of foundation. So again, if you compact the soil well, then the settlement will be less. Decrease the soil permeability also will be less. The water sometimes ingests to the soils and create problems. So that can be avoided. Stable against the volume change for other factors, wetting, drying, and freezing, thawing. Relatively durable and safe against deterioration. Increased slope stability and embankment, and can prevent the buildup of large water pressure that can cause the soil liquefy due to the earthquake. Okay? So these are the few things, the advantage of compaction. Lab test, again, we know already there are Proctor tests, standard Proctor tests. So R.R. Proctor is the one developed during the World War II. And then, so idea is we need to find out how much is the optimum quantity of water you need to add so that you can get the maximum density. Okay, and the impact compaction. So obviously, when you do this impact, so obviously this is called the standard practice impact compaction, and then depends on hammer drop, how many times the hammer. So most of the cases is 25 times. Weight of the hammer, height of drop, number of drops, number of soil layers, and the volume of the mold. So these are the different factors we need to check. So over here, this is the standard Proctor hammers. These are standard things. We have a standard mold is there. There's a we generally compact for standard Proctor compact in 3 layers. We have a standard hammer, 2.5 kg hammer, and 25 number of blows. We put it in 3 layers, and every layers you have to scratch it, and then you have to there are mechanical hammer. There are, manual hammer, so you can use. So manual hammer, we rotate it. Mechanical hammer is the mold is rotated, but the hammer is fixed. So we can do what type of test you need, what type of density you need. Accordingly, we can do the standard Proctor test or modified Proctor test. So over here, the standard Proctor, the difference, the mold is same. Hammer is, the weight is different. This is 2.5 kg, this is 4.5 kg. Standard Proctor is 30 centimeter height. This is 45 centimeter. Number of blow is the same. Standard Proctor layer, modified is 5 layer. And then the mold size is same. Obviously, it's more energy over there because you put in 5 layers. And then also here it is. And then weight of the hammer is also more. Okay. So the modified test was developed in the World War II and U.S. Army Corps of Engineers. So basically, to design the compaction required for airfield or support heavy aircraft. So that's the one most of the time, when you design something, heavy load, so we need to use the modified Proctor, or just for example, airport runway or anything. So, and also people are using this in the kneading compaction method. So again, it's a smaller method, it's a Hubbard miniature compactions. You have a mold, a smaller mold, 2.1 inch height and 1 inch diameter. And then also there is a spring, different types of springs are there. And then you have to press it. And because the height of the tip is very small, so we need to find out how much is the area. So most of the time we need to do different trial and error to find out, depending on what is the stiffness of the spring. So based on that, we can use the modified Proctor test, miniature Proctor test. So idea of using this miniature mostly for the laboratory test, we don't need too much of samples. Suppose if you're using chemicals or if you're using any polymers or others, we don't want to waste too much stabilizer or So here, so idea is only thing is you can put like a 5 layer. Sometimes you have to put 5 number of blows and then 5 layer. That'll be good enough. So depending on what type of spring are you using, you need to, depending on the stiffness, so you need to calibrate. And most of the time you need to do the same soil, check with standard Proctor and modified Proctor and see both should match. These are the two Proctor laboratory tests. One is standard Proctor and modified Proctor. And in the first one, the standard effort. So obviously, if you increase the standard hammer, so obviously the density is going to increase. And then optimum moisture content is shifts towards the left, right? So these are the different hammer weight, height of drop. People did some experiment for the ASTM. So again, what is happening over here? So the weight is the same, and then and for the same soil gradation, and then see what is happening over here in the modified and the standard method. Okay. So and then so obviously as I mentioned, you can easily calculate how much is the energy we're adding. So it depends on how much is the weight of the hammer, how much is the height of drop, number of blows per layer, and the number of layers, and divided by the volume of the mold. So you can easily calculate how much is the energy added. Procedure, again, everyone knows, but I'm just telling. So first thing is, if you're doing manually, so you need to do first 1, 2, 3, and 4, and then gradually go on. Oh, is it good? So then this is the manual procedure as I mentioned. But if you are using mechanical hammer, so then the hammer is falling at a fixed, at the same place, but the mold is rotating in that case. Okay, and then obviously you need to find out how much is the density, but that density is we are adding water into that, so you need to know how much is the weight of the soil inside the mold. The volume of the mold, you can find out the density. Density is equal to mass by volume. You can easily find out, but it is the weight density. But if you know after the standard Proctor test, you take out the soil sample and you put it in the oven and find out the moisture content. Then you need to find out how much is the dry density. Dry density is the weight density divided by 1 plus moisture content. So easily you can find out the dry density. So so the standard Proctor graph is basically the plot the moisture content versus not the weight density, the dry density. So this is a standard graph we are interested in, like you see the standard Proctor in the bottom graph is standard Proctor, and then the graph B is the modified Proctor, same soil. So modified Proctor, the energy is more, so density is increased, but at the same time, the optimum moisture content is decreased. It moves towards the left. And then we have degree of saturation, obviously 100%, that is 0 error line. So this line should be close to this line, but it should not be beyond this line. There's something wrong in that. So obviously these are the different degree of saturations. So again, you can easily draw this line from there, the unit weight of the soil, gamma D is equal to, you need to know the specific gravity, GS times gamma W divided by 1 plus E. E is the word ratio. Again, E is, again, you can find out E is equal to GW by SR, that GSW times GS, specific gravity of the soil, times W divided by degree of saturation. from there, if you for degree of saturation, SR, you see this is 100, you can use that SR 100 for the particular point, so you will get that graph. If you use SR is equal to 80%, so then you will get that line or different line, and then also the line of optimum. So as I already mentioned, so this is the graph, like what is happening. So in the standard proctor graph, initially the strength is density is increasing as you more water, and then basically the increase of density due to the compaction, because water will forming the coating of the soil particles, and then they are sliding each other with the hammer effect. So then they are adjusting themselves. But that's why the density is increased with adding more water, and then if you more water, then the soil particle will be replaced by the water, and then also density is decreased because the unit weight of water is less than the unit of the soil. Okay. So this is I already mentioned. So basically, we are interested in how much. So is go on increasing and then decreasing. So we are interested in how much is the maximum density and how much is that at what water content? That is the optimum water content or water content. So so obviously here I just want to tell like what is happening in the dry side of the optimum. So dry side of the optimum is basically so here in the weight of this is optimum moisture content. So what is the behavior of the soil on the left side of this, the dry side, and what is the behavior of the clay on the right side? Okay, or weight side of the optimum. So these are the different properties. Dry side is more random. As I mentioned, the clay is flocculated and more flocculated structures, edge to face, and the wet side is more oriented, like a parallel, more dispersed. Permeability is more permeable over here. Compressibility, more compressible in high pressure zone, more compressible in low pressure range, and the swelling more for high water efficiency, and the shrinkage more. The strength is obviously the dry side is higher, and then wet side is lower. So these are some of the things you can see more details, but from this Holes and Kovac, but I'm not going to go in detail. So most of the time, what you need to do basically for the single compactions, or I'm just going to go over here. So this is, you can see over here, the water density relations with 8 soil compacted standard proctors. This is using the standard proctor test. So one is, you see the well-graded sand with, SWSM. Number 2 is the well-graded sand, silt, well-graded silt with silty sand. Third is clay sand, okay, clay sand. And this is low compressible clay. Number 4, sandy lean clay. And then also, this is also low compressible clay. And then also low compressible silt. And this is highly compressible silt or fat clay. And this is poorly graded sand. SP is the poorly graded sand. This is number 8. So from a geotechnical engineer, so you can easily find out what type of soil we have depending on the soil from the standard proctor graph. Okay. So standard proctor graph, most of the time, this is more well-graded. Obviously, it depends on the particle size, right? The particle distribution graph, when is all the particle size in a soil, is all the different range of particle size is there. It's much better. We need that type of soil so that the bigger particles there and the smaller particle go into the the voids of the bigger particles, and then we can compact it. The void ratio will be less. You can compact more density. You can achieve more density. So poorly graded soil is not good. So it's a poorly graded means we are just all soils particles are the same or uniform. So that is not good. And then also depending on the soil. So most of the cases for granular type of soil, you add a little bit of water, then the changes is really drastic. For clay, the standard proctor graph is more flat. You just go increasing because clay can hold a lot of water. Is water it can so that's why it is go on increasing. It's more flat and then like this. So from this, you have an idea what type of soil is there. Okay, from the standard proctor test. So these are different properties of how much percentage of sand, silt, and clay, liquid limit, and plasticity index. And so you can easily find out how the shape of the particles, standard proctor graphs looks like. And also effect of soil type, we need to know the particle size distribution, we need to know the shape of the soil grain, You know the specific gravity of the soil, because the density is different. Gravity, gamma d is equal to GS gamma W by 1 plus E. So we need to find out the void ratio, amount of soil, and the clay type, clay mineral present. So these are a few things you need to check. So here again, same soil, but different effort, compaction effort. So first one is anything good? Everything? So laboratory compaction static test, 200 psi, modified Proctor. So everything is like a different effort, how the density is going to change. Okay, so you can find out from here. And so majority of the field compaction is controlled by the dynamic properties of this. So I'm just going to go now for the fine-grained soil. So what is happening in the microstructure level? Fine-grained, as I mentioned, this is mostly the clay type of soil. So you see here the compacted dry density, again, dry side and wet side of the optimum. So again, you see here on the wet side is much more dispersed, and the compaction on the left side, you see there is much more flocculated, and the strength is much more on the dry side. So, and then also you can see here how the permeability is going to change, with, if you do, this is a standard Proctor test. If you do the same moisture content, if you do the permeability test and the density, same density, you see the permeability is changing up to that optimum moisture, a little bit more than optimum moisture content. And after that optimum moisture content, the permeability is almost the same. There is no change. Okay. Field compaction, now this is the laboratory compaction. So basically using more compaction effort, then you'll get more density. Okay. So now to simulate the same situation in the field, there are different types of roller or compactor available. So again, this is like a shallow type of shallow compaction. Okay, shallow compaction. So one is smooth wheel roller. The next one is vibratory roller. Again, depending on the soil type, you need to use different type of roller. Then the third one is the pneumatic rubber tire roller, and the fourth one is the ship foot rollers. Okay, so the main limitation of these conventional compaction methods, the depth of improvement is limited. Although we use different type of heavy roller compactor, depth is limited. So when you need more depth of improvement of the soil, so then you need to do the dynamic compaction or blasting or any other method. So we'll talk about now what are the different methods available for the field and how much is the load you need to apply, what mechanism, and how much is the depth of improvement for every roller type. Okay. So again, when the depth is improvement limited, it is mainly used for the field, not for in situ natural geomaterial. So when you just, for example, you are constructing a new embankment, so you are using a field material and then compact it in different layers, and then you compact it. Okay. So sometimes, you have to put it in a certain layer. So mostly 30 centimeter, more, if you put more than 30 centimeter, the effect of this hammer, effect of this roller is not going to do that, So that's the, advantage. Then you have to go to the site and do the field test, right? So, I have one experience with this compaction, I used to work for a Dutch company when where the compaction, most of the time the compaction, people, okay, we did this compaction, in the evening time on whole night. Problem was, they used to do, instead of layer wise, they put a thick layer of clay and then just roll it. It's not going to occur, right? You're not get the exact density whatever you need. So what do you need to do? We need to do the field test and then check whether it is okay or not. Okay. So that is in Paradip. I used to work there, and then we used to do a lot of CPT and other tests. And then also one of the tests is like a field test using different methods. So I'm going to talk about that. So geomaterials should be within the moisture content, close to the optimum moisture content, or more effective. So we need to know from the standard Proctor test, what is the maximum optimum moisture content. You need to use that amount of water so that you can get the maximum density. And it is challenging to achieve uniform compaction geometry in a large area. So again, in the lab is more controlled test, and the field is a bit different. In the huge area, the road or any areas it is very difficult to check the quality. Okay. So first one is like a smooth wheel roller or drum. So here you see that it covers the whole area, 100% coverage under the drum. Okay, and the contact pressure is 300 kPa. So this is around 7,936 pound per square feet. Can be used for all type of soil except for rocky soils. You cannot use for rocky soils. Compacting effort is the static weight. Because of the heavy static weight is going to compact. Most common use of large smooth wheel roller is for proof rolling subgrade and compacting asphalt pavement. So this is the one. And the most important thing is here, effectively, it is compacts effectively for 20 to 30 centimeter only. Okay, 20 to 30 centimeter, it can compact. So it can, so that's why if you put more than 30 centimeter depth of soil, so it is not very effective. Okay, although it has heavy load, but it is there's a limitation, because of the static load. So this is smooth wheel roller, drum roller. Then vibrating drum or smooth wheel. So this is smooth wheel again, but it's a vibration takes place. So vertical vibration attached to the smooth wheel drum. And the best explanation why the roller is vibrating because it's an eccentric load. Arrangement occurs due to the cyclic deformation of the soil produced by the oscillation of the roller. So basically, two eccentric load placed into that because of that vibration, it vibrates. And here the load is the static weight. Earlier one, it was only the static weight, right? So it was the static weight over here. You can see static weight. This one we have static plus vibration. Okay? So this is suitable for granular soils. So granular soil is always suitable for vibration. So not that the compact, because if you compact it, then it will splash out the soil sample. So then, so this is the vibratory roller, how it looks like. Inside there is a off-center rotating weight. So because of that, it vibrates. This is the vibrating plate, the hand vibrating plates, how it looks like. Then now the question is for when you are using this roller or compactor, how many times you have to do it? Okay. So obviously, ideally, you have to do the compaction, and then when the compaction is done, you have to do field test, in situ test, using different methods. So most of the cases here in US, we use nuclear gauge. You can use any method, sand replacement, rubber balloon, water replacement method, or any method you can use, or simple core cutter method, you can find out how much is the density. So here in this case, you see the vibratory compaction for the sand, and you see the first graph in A, number of rollers. So it's 1 times. If it is do 5 times, if you do 15 times, you do 45 times. You see. So how the density is increased or decreased. So you see here the density on the in the top scale, the same unit, different unit, pound per feet cube or kilonewton per meter cube. It's not much difference if you see the 5 and if you see 15 or 45. Not much difference. So most of the time is optimum is if you do the same place like 1 time and 5 times is a lot of difference. But if you do 5 times, 15 times is not much different. That is the idea of this figure actually. And it says you see the 75% minimum required relative density of 75% is 5 roller passes. So most of the time, again, so we need to do like a 95% of the optimum, right? So 95% of the optimum, so that is the maximum. You will get the better results, depending on the site conditions. So over here, then the pneumatic rubber tire roller. So this is not that the whole area is going to cover, because some portion is, the tire, there is a gap here, right? So this is not covered 100%. So this is 70-80% coverage. Tires are closely spaced, 4 to 6 in a row. So depending on situation, the different company has different. And then the pressure is 700 kPa, is 14,600 psi pound per square feet. It's much higher contact pressure. Can be used for both granular and fine grained soil. So here the compactive effort is static load plus kneading action. So earlier one, normal one, the smooth roller is only the static. The second one, vibratory, static plus vibration. So now this one, pneumatic tire, static plus kneading action. Okay. So it can be used for highway fields or earth construction. So anything you can use for this. So this is how it looks like. The Caterpillar, Ingram, or different company has their different arrangement. Then the seafood roller. Seafood rollers, many round or rectangular shape, feet attached to the steel drum. Is covered is again 8 to 12% coverage, and contact pressure is 1,400 to 7,000 kPa. Is very high again. You see the 29,340 to 147 psi pound per square feet. And it is suitable, best suited for clay type. So if there is a clay, so use this seafood roller. Here, the compacting effect is static weight and the kneading actions. Static weight and the kneading actions. So, and as I mentioned, it's very effective for clay type of soil. Okay. And there's another one is not very common. Is a grid roller, grid or mesh roller, and it is compacted for suitable for weathered rock or well-graded coarse grain soils. Is very, very gravel, or boulder and cobble. Then it is good, and it is basically the weight is between 4.5 tons to 15-ton ballast. You can use for that to compact this. So again, so basically because of this weight itself, the static, and then also a little bit of kneading actions for this case. So this is here in US, most of the time, before this, any construction site, so people use this type of machine to just excavate a little bit on the top portion, remove there is the grasses, and then just cut the soil and then level it and then do the compaction. Okay. I don't know. So this is in our place is very common over here. So now another compaction is the intelligent compaction. So intelligent compaction is a continuous quality control. So normal compaction, what you do the compaction at the site, and then, okay, depending on the contractor. Now the contractor say we are done. So as an engineer, we need to go to the site and do the field test, okay, in situ test, and you check how much the density at the site compared to the lab, and then find out how much is relative compaction, right? So, but here in intelligent compaction, so instrument has itself the automatic measurements, and then the operator can tell with the color code. So there is a sensor in the machine, and then also and also the adjustment and optimization of the vibrating amplitude. You can change the frequency and the speed using a feedback control system in the machine operator to achieve the uniform compaction and desired target level. So the operator can control everything in a computer screen there itself, and then you can check, okay, when you do the compaction, it will turn to green. So when this green means, okay, you are done. So that is already instant quality check. So this is how it looks like. GPS linked to the site, so you need to know what area you are compacting. So that is through the GPS. You can find out an onboard computer screen. So again, you can get this type of what type of frequency, what type of weight you are using. So everything should be there, and there is a color code, so you can find out and change accordingly using this intelligent compactor. So there are different machine drive power, and then also the compaction meter value. So all these things you can easily find out from this. This is I've taken from this Venapusa's paper from Iowa State. So these are different instruments we have here in US available. The Caterpillar, Dynapack, Sakai, so all these instruments. So from there, easily you can find out as the compaction is going on, you can see the color change, and then if it is a green means you are done. So it's very easy for the contractor, the operator, and then obviously you need to go to check the quality control. So people have already did that, so it is much more convenient to use. But again, the thing is you need to have these type of facilities available to the contractor. So I'm not going to go in detail, drum roller, different type of drum roller, and then how that the different type of what they measure basically, So suitability of this intelligent compactions is similar to the conventional compactor roller, can use to compact the natural subgrade or filling range of cohesive to cohesionless geomaterials. So depending on the soil type, again, you need to choose that different type of roller. So I see interlinear compaction rollers are even more suitable for non-uniform subgrade condition than conventional compaction roller. So advantage of this, again, this is 100% coverage, the compaction properties, like a smooth drum roller, 100% coverage, and not like ship food or pneumatic tire. Helps the operator to identify which spot for further compaction or treatments, and then also the quality control and quality assessment. So, so you need to know, the comparator will know immediately which portion is weak, so then you compact more again. Avoid over compaction, so no need to do when the compaction is done. So no need to do the over compaction, just save energy and money, and reduce the number of passes. So again, depending on the soil type, right, and the water content. So when the compaction is done, how many passes, as I mentioned, like if you do 1 pass, if you do 5 pass, if you do 5 to 10, is not much difference. So if it is already 5 pass or 6 pass, it's already turned green, so meaning no need to do it again. Serves as a full coverage of quality control, quality assurance, minimize the need for field inspection. So again, obviously, after this compaction, also you need to go to most of the time, you have to go to the field test just to check whether the instrument is giving the correct results or not. But you need to have minimum, and the result is more efficient and uniform compaction. So limitation is the equipment is more expensive than the conventional compaction equipment. It requires managing and analyzing significant amount of data. Obviously, every time with the GPS coordinate, you take the data and then coordinate and find out more. You need more data. You need to analyze more data, and then this method are often required test strips for calibration of the targeted compaction values prior to production compaction. So obviously, you need to check first, for a particular site, you do this compaction and do the test again. So see, whether it is giving correct results. So these are the summary, as I mentioned, the field compaction. So in this figure, you see the 100% clay, 100% sand and rock. So what type of instrument roller? So seafood roller, you see that if it's a clay, 100% clay, seafood roller is more suitable. This is a static load, static weight and kneading actions. If it is a grid, static and kneading actions. If it is a vibratory, static and vibratory. If it's a sandy type soil. If it is a smooth steel drum, it's a static load again. So these are the different types of soil, and then what type of compaction, whether it's static, whether it's kneading, whether it is vibration, whether it is impact. So you can easily find out from here. Now the compaction control. So when you've done that compaction, so how you need to check? So obviously we need to do the test. So one test for 1,000 meter cube of compacted soil. And we need to check what is the minimum dry density. We need to check the range of water content. So to find out the field density, there are several methods. Core Carter method, sand replacement method, rubber balloon method, oil replacement method, nuclear gauge method. So nuclear gauge is very common over here in US. So again, everyone knows this, but in sand replacement method, what do we do? We used make a hole in the ground and then put a jar and then the sand. So most of the time we use the Ottawa sand. We know the specific gravity of the sand. We know the weight of the sand, and then find out. Basically, you take out the soil sample from here in this hole and then fill it with sand to find out. So basically, if you know the weight of the soil, if you want to find the density is equal to weight divided by volume. So the volume is over here is irregular volume, right? So now we need to find out the volume of this irregular hole using this standard Ottawa sand. We know the weight of the Ottawa sand. We know the specific gravity of the Ottawa sand. You know how much the sand gone inside, and you can find out the volume of that. So if you know the volume of that hole, you can find out how much is the weight of the density of the site. So that is the weight density, but again, you can find out the dry density if you know the measurement. Water replacement test, again, same thing. We just fill it with water. Okay. Then rubber balloon test. Also, is an instrument over here. You need to pump the balloon, rubber balloon, and the balloon will be, instead of earlier one, you fill it with sand. Now the balloon will be inflated into that hole, and then it will be filled with water. So we can find out how much is the water inside that hole. So you can find out, the specific gravity of the water is 1 gram per centimeter cube or 9.81 kilonewton per meter cube. If you know that, you can find out the volume of this hole. If you know the volume of the hole, you can find out weight divided by volume, so you can find out the density. So this is the rubber balloon method. And this is a nuclear case. So obviously there is a photon source, and then it's very easy. Just go to the site, and there is a smooth surface, and then compact the this rod with this rod, and make a hole into the ground, and then just place that on the top, the instrument on the top of that, and then it will immediately give you how much is the weight density. And then also this is the one in place if it is a rock filled soil. So then you need to use like a water replacement test. So you need to put a polythene over here, you can see, and then use the water, and then density of water is known, so you can easily find out how much is the density. So these are all like a field density method. So basically what you need to do, from the lab test, you know the laboratory density and optimum moisture content. And then you go to the site using different type of compactor and stabilizer, different type of roller and compactor. And then you just take out the soil sample and check how much is the relative compaction. So, and then find out if it is relative compaction is 90 to 95%, then you are good. So basically the lab test is a control test. You will get all the time, you will get the maximum density. Same soil if you're in the field, because here is huge area, we have roller and compactor, using, this is not very controlled test. So basically if you get 90 to 95% of that, the lab density, then you are good. So what is the relative compaction? Relative compaction, how much is the density at the field divided by how much is the maximum lab density times 100%, you will get that. So in the compaction system, in civil engineering practice, what you do, design problems. So we are doing earth dam, highway, railway road, and levees in a structural field. Design engineering properties, so engineering properties, strain, compressibility, all this stuff. Laboratory test, and then you do specify design values, how much the relative compaction is required. So you need to do that, and the compaction specifications, compaction control test you need to do, and then finally, the quality control. So if you go to the site and say, okay, this is 90-95% of the lab, then you are good. So again, just for example, over here, 3 hypothetical field compaction tests in the same soil, but different compacting effort. Okay. So over here is the dry density in y-axis, and this is standard Proctor test, right? Proctor compaction test and water content. So there are, you see the different. This is hypothetical test, and then but different, same soil but different compacting effort. So you see that. Graph 1, obviously you put more energy, that's why the density is increased, like a modified Proctor. This is number 2. Number 3 is a less effort, and then this is the line of optimum. So this is the line of optimum moisture content. So optimum density, you just put the line of optimum. This is the 100% saturation line. So here, so from here, what is the most water content you need to use? Okay. So just for example, if you see the maximum density is achieved is for this graph 1, right? Maximum density is achieved graph 1. And this is the line for 90% relative compaction. Relative compaction is 90%. So now, what do you think we should use that water content to at the site? Anyone can tell me what should be the good range of water moisture content you need to use? Can anyone tell me the range of moisture content you need to use at the site? This is the lab test. One. Can you hear me? So here you see what you see over here. The water content is number 1 is A. So this is the moisture content is A, and this is number C is at the x-axis is C, correct? So that is the range of water, you can use A to C, but in the field, if you see this C is basically, C point is, if you consider the first graph, that is the wet side of the optimal. The soil will be much wet. So ideally, you can see here, the same soil, optimum moisture content for C is here, this is point B, correct? So ideally, you should use close to basically from the moisture content from A to B range. If this is the moisture content, that is much better. Or you can use the optimum moisture content for one over here, one from here to this point B. What is the water content? So this will be the good range of water you can use at the field to get that the maximum density. Okay. So variable is the vibratory compactions. Again, densification of the soil, compaction of the compactor, we need to check. Characteristics of the soils, we need to check. Initial density, grain size, and water content. Construction procedures also we need to check. So a lot of things we need to check during that at the site of vibratory compaction. I'm not going to go in detail over here. So idea is, so laboratory tests are conducted to basically how much is the maximum density and water content is required for that particular soil, and go to the site and add that much quantity of water or moisture so that you'll get the maximum density. That's the purpose, right? End product specification. So we need to check specification used mostly for the highway and building and foundations. So basically, you need to check if the ready compaction is 95% of the lab, then you are good. Care the results only. Again, method specification is typically used as large compaction project. So basically, what you need to do, type and weight of the roller, number of roller pass, as well as the lift thickness and the specified maximum level size of the material may also be specified. So this is method of specification. And the relative compaction, as I mentioned, there are you can find out how much is the density, dry density at the field divided by how much is the maximum dry density at the lab times 100. You can easily calculate. There are a lot of correlations that are available. Relative compaction with the relative density over here. The relative density is E max minus E divided by E max minus E mean. So how much is the maximum void ratio and minimum void ratio? If you need to know, then you can find out that relative compactions. And typically, as I mentioned, that 90 to 95% relative compaction. Then, so basically, that up to that portion is basically shallow compactions. And I mentioned shallow compaction can be achieved using different type of roller compaction. And the load is basically, it can be static, it can be vibration, it can be leading action, or it can be combined, or it can be mostly, so all these different types of load. Now, blasting or control explosions. So blasting or control explosion or blast dissipation is detonating a small explosive charge using a dynamite at certain depth so that the ground surface is saturated. It can be saturated or loose or cohesionless soil, such as, that densification of the soil takes place. Okay? So grain size is suitable for the blasting. It's the same as compaction for vibrations. Okay. We will talk more about that. Lateral spacing of the charge varies from, at what depth, lateral distance you need to put that. So varies from 3 meter to 9 meter, the lateral charge. And usually explosive charge are placed at a depth of 2/3 of the thickness of the soil layer required to be compacted. So this is very important. 2/3 layer of the thickness of the soil layer required to be compacted. So we need to put that explosive and that at that level. 3 to 5 successful detonation.
नहीं अभी तो टाका आज कटा हुआ है, ठीक है ना, अभी तो ही चल रहा हो, हाँ चल रहा है.
So usually 3 to 5 successful detonation are usually necessary to achieve the desired compaction, and also the compactive effort up to relative density. Do this blasting, obviously, you need to check that explosive charge are buried at a depth. and detonated precise timing to achieve the soil compaction. So while doing that, you need to use the multiple charge of details a close time frame. So you need to have few, at certain spacing, you have few charges. And it causes, if it is saturated soil, it causes liquefaction of the soil. So you can see that charges point, the water will come out because the pore pressure releases, and followed by dissipation of the pore water pressure and leads to consolidation over several hours. So again, consolidation takes place. Advantage of explosive compaction is can reach far down 50 meters. So it's really quite a depth. And also we'll talk more about that, dynamic compaction. So, but this is blasting. So what happens over here, if you do the blasting, breaks down soil structures, reorientation of the soil taxes takes place, and volumetric reduction of the soil up to 10%. So these are the things happen. So now, how much? So if you put the blasting, control blasting, how much the area of influence will be? That depends. The sphere of influence using by this equation, you can find out the Mitchell's equation, 1970. WEX, that is the weight of the explosive you used, and then C is the constant you can use for, and then you can find out how much the radius of influence. Because if you know the area of influence, you can find out how much at what the spacing you need to use this for the blasting. So these graphs will give you a guideline like how much. So this is the Mitchell test, uses 2.5 kg of charges of galamite. Number one. So again, you see here M1 and M2. These are the different locations, and then different tests they did, and then you see for test 3 and 4, more tests is more settlement, obviously. And then in Netherlands, you use like a charge of 10 kg of TNT, that's trinitotoluene, and each depth of 15 meter depth defall and surface space of 15 meter apart. So if you do that, the spacing, and then you can get that how much the maximum settlement you require, you need it. Now, so I have just one question now over here. Now I'm going to talk about the deep compactions. So I want to ask, like for the compaction method you use. Like one is the core cutter method. So you go to the site, use a mold and push it into the ground using a dolly and hammer, and then take out all the soil. Mold plus soil, you just find out, take the weight of the mold plus soil, remove that weight of the mold, the weight of the soil, the volume, you can find out the density. Same thing you use for sand replacement, you can find out how much is the field density. If you use rubber balloon method, you can use that. If you use nuclear gauge, you can use that. So do you think that, so every method, ideally, it should give you, whatever method you use, ideally, you should get the same density, correct? What do you think? It should be you should get the same density, correct?
Ideally, yes.
Ideally, yes. That's good. But the thing is, if you use different method, like if you use rubber balloon method, just for example, if you use sand replacement, do you know which one is giving higher value? Will give higher value?
Core cutters.
No, I'm just telling just rubber balloon and sand replacement. So what do you think?
Sand replacement will give higher value, I guess.
No. So, I had experience, that in Paradeep, that now is Indian Oil Refinery is there now. So we used to do a lot of tests, that sand replacement, our client was EIL, and then we used to do a lot of tests. So most of the time, this rubber balloon gives higher value compared to the sand replacement. So we used to do EIL, used to do the sand replacement, and then both tested we used to do, and then also we used to do the CPD test, the cone penetration testing later on. and then we check the density. So again, this is depending on your need, you can use it. What method do you need to know? But mostly core cutter is the easiest way, and you can find the actual one. But my experience, I'm just telling you, like a rubber balloon gives higher density than sand replacement method. But obviously here in US, most of the time people they don't do this. Just nuclear gauge. It's easy and quick. So now I'm going to talk about this dynamic compaction or deep dynamic compaction. So it depends. So it's very, very simple test. So shallow compaction, we mentioned that there are different type of roller, and we mentioned there is a limitation. It can go up to a certain depth. So when you need higher depth, so when you have to do either dynamic compaction or deep dynamic compaction. So deep dynamic compaction was first used in Germany in 1930s. So it's a very simple method. So which heavy weight known as pounder just suspended from a crane and just drop it. Okay, it's very simple. And then how much the depth of densification is going to occur, it depends on is in meter. There's the equation. D is the depth of densification approximately square half 0.5 times square root of WH times H. So where WH is the height of the dropping weight, okay, and then H is the height of drop in meters. So if you do that, you can easily calculate how much is the depth of densification. I put some of the YouTube link. Anyone can check. It's very simple. Here, the impact. So basically, what happened is you just drop the weight. So impact produces the shock waves that causes densification of the unsaturated granular soil. So again, the surface wave, Rayleigh waves, so all these things is going to occur. And then if a saturated soil, granular soil, the shock waves can produce, obviously, and then it's partially liquefaction of the sand may occur, and the conditions similar to quicksand and followed by consolidation and rapid densification. So this is happened when you impact the soil. So how that the shock wave basically propagates and densify the soil. The equation is the same again. How much is the, you need to know how much is the depth of improvement. So D is equal to N times square root of WH. WH over here, the weight of the pounder and the height of the fall. There is a table for N. It's at different factors. So you can easily calculate so what type of soil, how much will be the depth of densification. And you can vary so many things. You can increase the height of the fall. You can increase the weight of the fall, all these things. And easily you can calculate how much is the depth of densification you need. So this is important parameters you need to know. So basically you need to, there is a huge crane is required to lift 10 to 40 tons of the pounder to height around 25 to 100 feet, and then drop this weight onto the ground. Okay. So cost-effective method to densify loose sand and silty soil up to 15 to 30 feet deep. So 15 to 30 feet deep if you want to improve the strength of the sand. So this is a good method. So you just drop it. So degree of compaction again depends on the weight of the hammer, height of the hammer drop, and the spacing and location. So what is the spacing? So there are different things we need to check. There are primary impact, there are secondary impacts, all these things. And the deep craters are formed by tamping. So and then later on, this crater, when the compaction is done, then later on this crater will be filled with sand after every passes. Okay. Suitability again, the loose and partially saturated field, saturated free draining soil, silt and plasticity index less than silt with plasticity less than 8. This is good. Clay soil with low degree of saturation, and then also generally not recommended for clay soil with high plasticity index greater than 8. So it's not suitable for clay. Reduced effectiveness, the water table is within 2 meters of the starting level. So the water level should be below, so that is good. And this is economic for sites more than 5,000 meters square, and a certain clearance is needed, because if you are doing this impact close to a house or anything, then that may create a detrimental effect to the existing or nearby building. So this is in Shanghai, that the deep compaction is a huge site. They are using this. So as I mentioned, the N value over here, D is equal to a depth of improvement or depth of densification is equal to N times square root of W times H, where N is the coefficient that accounts for soil type of pounder, falling mode, so all these things. So again, different people have given different N value for different type of soil. So we need to check that. This will give you a guideline to select what type of, how much the depth of improvement they need. And then you can use these values, N value, to calculate how much is the depth of improvement. So N, the variation of N attributed to the efficiency of the drop-off mechanism of the crane. Total number of energy applied is 0. So type of deposit being densified, the presence of energy absorbing layer. So a lot of things you need to check. Contact pressure of the tamper. So all these things you need to check. Okay. Then phasing of dynamics. So obviously here you can see here, this is so the dark one over here, this is the main first phase compaction of the deep layer. The first layer is the dark one, dark yellow color. And then first you do all the dark one, and then you go in between over here. This is the second phase, a compaction of intermediate layers. So do this compaction, the second phase. And then obviously you are ignoring this phase, correct? The square one is not everywhere. So you need to see for one influence, one impact. So how much is the area of influence? So we need to check that, and then and that is good enough for the improvement. So over here, the property changes with depth. Obviously, as I mentioned, so it is going like a so like as a cone type of stuff, So when you apply load in a soil stress, like a 2:1 or 1:1, like a load distributions, it's load like that. So it's ignoring phase one. There's the first phase, and the second phase is the second one, over here, and how the density is increased with these impacts. And again, there's a square pattern or triangular pattern are commonly used depending on how you're going to do that. So again, as you have seen, over here, this is a square pattern. This is a square pattern, so it can be triangular pattern also. All right. The crater depth. So when you impact it causing a crater, so high energy applied can result in a crater of 1.2 to 1.5 meter deep. Crater depth should be limited to height about tamper plus 0.3 meter. The depth of loosened upper zone about crater depth again, and then the loosened soil zone should be densified by ignoring pass. Okay, so a few things you need to check, and this is how it looks like after dynamic compaction. As I mentioned, it should be filled with. This is the hammer. It should be filled with sand later on, and place your actual structures. So what is going to happen when you impact it? So how much is the peak particle velocity? We need to check. So we need to calculate the peak particle velocity. High energy impact on the ground increases environmental impact, mostly vibration, noise, and lateral ground movement. So basically, how much the Rayleigh waves, different waves. So upper limit of peak particle velocity, Main et al. 1984. So peak particle 70 times square root of WT HD by X dP, power 1/4, power 1.4. So this is stamping weight, drop height, drop height, and the distance from the drop point. So you need to calculate all these stuff. So find out, sometimes the peak particle velocity is very important. So, you have an idea. So you have, so different thing for different soils, peak particle velocity and the energy you can find out. So it is sometimes this peak particle velocity is very disturbing. It's not disturbing, strongly perceivable, and the slightly perceivable. So depending on the situations over here, so how the typical particle velocity is 20 to 40 millimeter per second. It is good for structural or commercial building. The threshold velocity, it should not be more than that. Residential construction, it should be 5 to 15. And for sensitive, it should not be 3 to 5 millimeter per second. So impact, we cannot just, dynamic compaction can be used in that area. So now the thing is, sometimes if you have a building over here, you are using a tamping. So sometimes you have to do the cut-off wall, cut-off wall, so that the velocity will not travel. You need to cut a trench so that the wave will not move, okay, to the building. So this is good. Sometimes, so this we generally use this when you are designing a machine foundation, right? So foundation, so we need to do a cut-off trench so that the vibration will more. So we call it the vibration isolation, right? The same things you can do that. If you want to use this dynamic compaction, and there is a building nearby, so you need to use this cut-off trench. Okay, so these will give you an idea. So this the range of treatment depth varies with initial strength and soil type and energy input. So you can easily find out from here if it is a loose or weak soil. So and then how much energy you need to put, and then again everything is related, right? So how much the D is the depth of densification, how much is the weight of hammer, and how much is height of foam. So all these things are related. So this will give you an idea. And then, so how much the energy you need, how much the depth densification you need. So if it is a weak soil and if it is a steep soil. So if it's a weaker soil, you see, you need more impact, or you need more energy. So there are many factors affecting the dimensions. So again, the type and competition, the competence of the surface layer, position of the water table is important, number of drop at each location is important. And the knowledge of depth at any stresses impulses the vital factors, so it's very important. And also kinematic energy. So most of the time, there are different criteria. In the Britain, just for example, velocity is 30 mile per hour is a mini scale method. Effective depth of treatment 4 to 6 meter. Velocity 50 mile per hour full scale method. So and then this is treatment method is 6 to 8. So these are the few things you need to check. And so dynamic compaction, few things you need to check over here. I just want to mention that generate a surface wave. So obviously when you impact, because of impact is a surface wave, dominant frequency of 3 to 12 hertz, and vibration generates 3 types of waves: compression, shear, and Rayleigh wave. Rayleigh wave contains about 67% of total vibration energy. So this is very important, the Rayleigh wave, and becomes predominant over other waves. Other wave types comparatively small distance of the source. So the Rayleigh wave is important. And the Rayleigh waves are the largest practical interest for the design engineers because the building foundation are placed near the ground surface. So the top surface, Rayleigh wave is important. And there, so peak vertical velocity is very important there. So peak vertical velocity, the maximum velocity recorded at any three coordinates axis. So we'll see the figures, and then and the measurement of the vibration is necessary to determine the risk of any nearby structure. So you need to know that. So this will give you a guideline, all these graphs. And vibration can estimate through empirical correlations measured with the help of instrument, like a portable seismograph or accelerometer, or velocity transducer, or simple LVDT. Okay. So this will give you a guideline, like a peak particle velocity and the scale distance. And the frequency of the Rayleigh waves decreases with the increasing distance from the point of impact. So as you go far distance, its impact is less. And the relationship between the peak particle velocity and inverse scale distance is shown graphically over here. You see the scale distance and the peak particle velocity. So this will give, you can adjust everything depending on the instrument. So you have huge cranes. Suppose sometimes you don't have huge crane is available. So what you need to do? So height of fall will be less, correct? In that situation, so you can use the weight of the hammer itself, okay? And then you can do, it will be the same thing. So how much is the energy, like a kinetic energy, right? So WmgH, the simple thing. So, and then the peak particle velocity, you need to check how much is the velocity travel, and then depending on that, whether it is detrimental to the adjoining structures, that also you need to be that will give you a guideline. So I'm not going to go in detail. So over here you can read that. So you see the upper vibration limit of the vibrating operator is frequency 30, and the lower is 50 hertz. So this is the limit generally used. And in addition, the magnitude of vibration, typically frequency range of 5 to 15 is potentially 5 to 15. Lower frequency is potentially damaging the structure, and that is particularly noticeable to human beings. So basically, the lower frequency is not good. So this will also give you some guide. Here is the same thing again, the structural damage. Earlier I mentioned 50 millimeter per second. Minor architecture damage, if the velocity, peak particle velocity is 10 millimeter per second. Annoyance to occupants is like a, the existing building is 2.5 millimeter per second. So again, three main things. Vibration becomes a problem when the three main methods to reduce their effect. The first thing is to simply reduce the height of the drop. So depending on the situation, and compensate by increasing the number of drops. So you just reduce the height of drop. But number of drop is more. Same thing like a standard Proctor and a modified Proctor. So the modified Proctor, the weight is increased, and then also the number of layer is increased, right? So number of drop is all the same, 25. So these reduces both impact energy and the penetration of the stress impulse that may attain an unaligned or a dense stratum. Second method, reduction of utilizing smaller weight. You can reduce the small weight. And the third, to excavate a cut-off trench, as I mentioned, so that you just cut off the velocity is traveling, right? The horizontal travel to the ground. So obviously, if you cut off trench, that will basically isolate the vibration. Okay. So now there are special deep compaction techniques. So we have fiber compaction method, we have fiber replacement method, you have fiber composer method, and then also cased borehole method. So there are several methods. So first thing is we talked about like a normal compaction, normal different type of roller compactors. There is a limited depth. And then we talked about dynamic compaction. So dynamic compaction, because of dynamic effect, can go higher depths. And also we mentioned that control blasting. Okay? So now the special compaction, the fiber compaction method, fiber replacement, and fiber composer, and then also cased borehole method. So here, first one is the fiber compactions. So fiber compaction method is the fiber compaction method used to densify the cohesionless soils or granular soil using a fiber float. So this is a fiber float. So we'll see some more picture. So basically, what is happening? You need to make a borehole, and then using a fiber float, insert it into the soil, and then put gravel from the top, and then you can compact that gravel. So the fiber compaction is suitable for granular soil. So this is if you construct like a stone column, you can use this, the exact same method. Fiber compaction is suitable for granular soil with silt content up to 10 to 15%. So this is really suitable for gravel type of material. The presence of fine in exceed of 20% may, so if the fine content is more than 20%, it's not good. It's not effective method to use this fiber compaction. So again, as I mentioned earlier, the vibration is good for granular type of soil, a sandy type soil. Same thing also, the vibro, so obviously is suitable for granular type of soil. So SPT value of 5 to 10 near surface is not applicable for clay. So when SPT value is on the surface is low, is not applicable. Again, it's not applicable for clay. Fiber compaction can be used to compact granular soil up to a depth of 40 meters. So it can use up to 40 meter depth. And using a fiber float, which sinks the ground under own weight, 4 to 8 ton of weight, and length is 2 to 2.4 meter, 2 to 4.5 meter, made with assistance in water and vibration. So there are this fiber float, there is a water jet is attached to this. So most of the time when it's go inside, it's the water jet, and then it's making a hole, it's go down. And then the gravel is added to the top, from the top, and then it just vibrate, the ground, basically. So fiber compaction method. So compaction is selected location using a vibration and vibratory equipment results in compaction at larger depth. So you can go up to 40 meters. Zone of compaction around single float is a function of type of float. So again, what type of float you are using. And the success of in situ densification depending on the grain size division of the in situ soil and the backfill soil. So this is important for the what type of soil there at the particular site. The use of drone size analysis of soil to decide on compactability. Again, obviously the compaction is depends on the well graded or poorly graded. All these things you need to check. So base suited for, obviously, as I mentioned, so it is suitable for cohesionless, clean cohesionless soil with certain percentage limited percentage of fines allowed. As you mentioned that ineffective when the fine particles percentage passing is less than 200 millimeter sieves or 0.075 millimeter, 0.074, it should be 0.075, is more than 25%. So, and then ineffective if the situation due to the decreased impermeability of the material is excessive fine. So again, that is also not good. So, and then as I mentioned, using a fiber float, it gives the horizontal motions from the vibrator inside into the ground. Okay, so I'm just going to show you some pictures. Applicable soil, I'm going to go in detail. So this is fiber flotations. This is the particle size range. So basically, you see here the gravel. The most desirable soil range is gravel to sand. That is very good to use this fiber flotation technique. I'm going to go. So this is fiber flotation techniques over what you need to do. So basically, it's a technique in situ densification, thick layer of loose granular soil. And again, also it's developed in Germany. So what you need to do in a fiber float or vibrations, 3-element extension tubes and the crane and jet water supply and pumping. And so basically, in front there's a jet water supply, so it can go down and then it can vibrate. So over here, so obviously, so first you make a hole into the ground, and then it can vibrate, and then add from the top like a gravel material, and then it vibrate horizontally. So and then it can forming a column basically, sand column or gravel column, okay, or stone column you can say. This is very common. This is the picture I took it over here. So if it is a clay type of soil, this is sand column, but that stone column construction site. This is when the soil is good, clay type of soil, using this boring method, take out the soil sample and check it so that the sample will go, and then after we make a hole, just cover it. So this is the spacing between the center to center of this different stone column. And then using this vibrator, at every steps and put a gravel. Most of the cases in the US, we use that CS6 gravel material for this stone column or fiber compaction technique. And then how it looks like. So this is a fiber float. So it really vibrates. And at the point over here, there is a holes and the water nodule. So it can really vibrate and then compact the gravel. Okay. So fiber flotation method. So what you need to do, first thing is a stage 1 is a jet of bottom of the fiber float turns in the lower into the ground. So obviously there's a water jet, so that will create a hole. And then water jet creates a quick condition of the soil, allows the vibrating unit to sink to the ground. So the vibrating unit sink into the ground. And then what you need to do, add a gravel material from the top, and then it vibrates. So basically, it was up to here in third step. And then you just compact this, and then from the lower part, and then lift it up. So after compaction is done, you just lift it up, and then you're forming the solid column, okay, on soft clay. These are the different vibrating units. So I'm not going to go in detail. So different 100 horsepower electric unit, 30 horsepower electric unit. What should be the vibrating tip? Eccentric load. So basically, because of eccentric load, it vibrates. And then what type of pump you use. So all these things. This is from the Brown 77. And then also we have the lower follow-up pipe and extension. So obviously, you can use different type of diameter and weight. So how you are, again, nature of probe spacing. So it depends on, and the blue color is the probe spacing where you're putting that probe, and then you can do it. So basically, this is like a triangular type of arrangement. If you see blue dotted line, if we add this, so this is basically the triangular, and then the sample is compacted over here in the whole area. So for stone column, you need to know later on the how to area replacement ratio and other things, but here you need to do much over here. Then fiber compaction now is a fiber replacement. Okay, so fiber replacement method is used to improve the strength of the cohesive soil when basically it's for clay type of soil. So we need to do. So what you need to do to achieve this, you use the vibrating probe similar to the technique. It's a fiber compaction, but the probe is allowed to penetrate the soil and does so by displacing the soil radically. So that's how you do. So it can be either wet method or dry method. So both method can be used. And when you use this soil, when the undrained stem, the soil is more than 40 kilonewton per meter cube. So that is. So obviously, what you need to do is a clay type of soil, cohesive soil. So when you make a hole, it should not collapse, correct? So and the strength of the clay is at least it should be the compressive strength or sorry cohesive strength should be at least 40 kilonewton per meter square so that it can stand at its own. Okay. So fiber replacement again. So this is replacing. So what you need to do, you take out the clay and then replace it. Okay. The stone columns extend the range of soil that can be improved by vibrating technique, including cohesive soil. And then also the cohesive soil is basically you are densifying the soil on the side. So basically the consolidation takes place or compaction takes place. Densification or reinforcement of the soil as a compacted granular stone columns is accomplished by either top feeding or bottom feeding. Again, I'm not going to discuss this top feeding and bottom feeding method. I think Dr. Srileja, maybe Dr. Bawal is going to explain this method. And then the cohesive soil mixture, the soil generally do not densify easily when subject to vibration alone. So again, so that is the difference between this replacement and also that vibration. So over here, the fiber compaction, why I need to use and fiber replacement. So obviously, fiber compaction is good for sandy type soil or gravel type of soil is excellent, and fiber replacement this is not suitable. For sandy type soil, silty sand less than 20% fines. So again, I'm talking about fine means particle size is less than 75 micron or whatever the passing number 200 C, meaning less than 200 0.075 millimeter. And then this is good fiber compaction. This is good for fiber replacement. For silt, it is fiber compaction is poor. Fiber replacement is good. Clay is not applicable. You cannot apply because no vibration. So fiber replacement is good. So these are the different things. Which method is suitable for fiber compaction or fiber replacement? So and then fiber composer methods. This is a popular method in Japan, used for stabilizing soft clay in presence of high groundwater level. So you can use that, resulting the piles usually known as sand compaction piles. So most of the cases is sand compaction piles, or here in US most of the time we call it the drill pyre or pyre. And then a heavy of 0.4 to 1.5 meter diameter casing is required to driven down the required depth, and by a vibratory hammer located at the top of the casing. So sometimes, again, if you're using sand, so obviously if you're in clay, so obviously what is going to happen, then you need to use a sand geosynthetic casing so that it will not mix with sand and clay or sand and gravel. And the spacing is normally between 1.77 to 2.5 meter. So this is the particle size range for fiber compaction and fiber replacement. So mostly the fiber compaction is the sand and gravel type. You see the range over here. And the fiber replacement is replacing. So you can do mostly for the clay, so you can replace any type of clay and then or gravel and then you can either using top feeding or bottom feeding method and you compact it. Only thing is depending on how much is the stiffness of this of the clay. If it is too soft, so then there is no lateral confinement. The problem is if there will be settlement and then also there will be bulging of takes place on the steel. So these days that's why people are using geosynthetic encased stone column or geogrid encased stone column for this fiber replacement method. Okay. So when using fiber compaction, it is necessary to supply additional material to achieve the required densities. To fill should be sufficient enough to transmit the vibratory action to the surrounding in situ material. Coarse granular material with little or no fines provide the best materials and allow faster rate of compactions. And also the Brown also developed a rating system for the imported fill material. So again, sometimes we need to have that the granular fill to fill the hole, correct? So sometimes you need to transport that gravel type of material from a far distance. So sometimes if you find some locally available materials, so these days people are using even recycled material into that as a fill material. And then also the Brown's system, he developed a number called the stability number. So it is shown in here. Suitability number, how much? So again, is the equation is 1.7 square root of 3 by d50 whole square plus d20 whole square divided by 1 plus d10 whole square. So obviously, d50, d10, d20 from the particle size division graph, you can find out like a 50% finer, how much is the percentage, the particle size. 20% percentage finer particle size. So 20% come down the how much is the particle size. Millimeter, so you can find out that, and D10. And if you know this D50, D20, and D10, use this equation, find out how much is the stability number. So if it is a lower number, it's good. So if you get 1 to 10, this is excellent material, gravel materials, gravel type of materials. If you get like a 10 to 20, is good. If you get like the higher value is not very good. So that's the thing. For the backfill material evaluations according to the Brown stability number. All right, I think that's all for this up to the different compaction techniques I just explained. So I have gone really quick, so I don't know how much time we have. So we have Dr. Senthil or Chure, can you just tell me how much time you have now?
Yes, sir. Time is almost completed, sir.
Oh, okay. Yeah. So I have just gone very quickly because the syllabus I have given to me, the syllabus given to me is really, there's so many material. I have to go. Otherwise, I have just gone right so fast. So otherwise, I cannot finish it. So I just, if you need, because there are a lot of things we need to know and we need to go more detailed. And then maybe we'll solve some problem maybe tomorrow, some assignment problem or some tutorial problems I'll be solving. So anyone has any questions? I don't know. I mean, there are so many topics we
Sir, I have one query. In the deep dynamic compaction that you mentioned, like it seems to be very much in nearby structures, it will impact significantly. So, like one of the trenches method that you explained, but how much distance we should think about wherever it is being applied, deep dynamic compaction, sir?
Okay, so that's one again. I can go much more detail. I mean, that one, most of the cases when you design like a machine foundation, just for example, right? So we need to do the vibration isolation, right? So it depends on. I can solve some problem maybe, or I can send some material to you so that it will be much easier. With the I cannot tell exactly at this point on the top of my head, but I can send some material so that you can. So basically here, whatever we explain is just guidelines. All these peak particle velocity and other things, and the energy, you can readjust the weight, hammer, height of drop, all these things, and then so this will give you a height guideline and also what type of frequency you are using. So that will tell you, and then which one is detrimental effect. So so you need to check all these factors, and then you need to see, which one is best suited for a particular site condition.
Thank you so much, sir.
Yeah, I can send some material to you, so that you have an idea.
Sure, sir. It will be really helpful.
Yeah.
Thank you, sir.
Yeah, I mean, here in these classes, I mean, this course is very basic. I just talk about the compaction things, the very basic, that simple thing to, again, different type of roller compactors. Everyone knows, but again, how much is the depth and the deep dynamic compaction, and then also that fiber compaction and fiber flow. I mean, we can take fiber float and fiber compactions in 2 days, but because of limited time, we really cannot do much. Any questions? I know it's very quick and it is just like a one-way teaching or explaining something, it is difficult. Several topics and then also less time.
So, sir, I think there is no more questions.
Okay. All right. Thank you so much, everyone, for listening to me. All right.
Thank you, sir. Thank you so much.
Okay.
Yes,
Thank you,
sir.
sir. Thank
So
you.
tomorrow morning, that means Indian time, IST evening 6:30. Is it okay, sir?
Thank you, sir.
I mean, what do you think? I mean, you guys decide. Okay. Today I was prepared for evening time, but we suddenly, in the morning time. So it is
Right,
up to
sir.
you. Whatever you suggest, whatever is the best suited for the student, so I can, or the participants, so I can do that. Okay.
Yeah, I think this time would be very good, sir. Maybe evening 6:30 because many people maybe they're coming
These
out
times,
from the office.
these times are really good, sir. Actually, I am Dr. Shashank from NIT Uttarakhand.
Okay.
In the
Okay.
morning session, we are also engaged in various activities and
Okay.
administrative duties. So in the evening period, it will be it becomes convenient to attend the session.
Okay. Whatever, I can do that. So
Yes.
tomorrow then evening in here
Yes, sir.
US evening time, right?
Yeah, IST 6:30 would be fine, sir.
6:30.
Same time, sir. Same time.
Yeah, same time.
Like today.
Same time.
Senthil,
Okay. All right.
please ask the convenience of the sir.
No, it's fine. I'm fine. I know.
No, actually, I asked sir. Sir is okay for anything, sir. As per the participants' convenient, he's suggesting.
Yeah,
time.
yeah. I mean, I'm fine with that. So it will be maybe 11:30 night. So it doesn't matter for me. Because I also do here, administrative stuff. Here it will be difficult for me also, I mean, one day, today is done, but, for the next days,
Okay,
so it is
okay,
fine.
sir.
I mean, whatever you say is, you guys, send an email to me and then I can, okay?
Sure, sir. Right, sir. Okay, okay, sir.
All right. Thank you so much.
Okay, sir.
Everyone.
Thank you,
Bye.
sir. Bye, bye, sir. Vipendra, madam will be joining.
Yeah, okay, sir.
Hello, ma'am. Yeah,
Shall
yes.
I start now or
Good evening, ma'am. I think, ma'am, we can start now because already 9:40. It's
Yeah,
very
yeah, okay. I will start.
yes, sir. Yeah.
Hello, hello, ma'am.
Yeah, I'm here. I'm just going to share my screen.
Okay. Parvesh sir, are you listening? Parvesh sir?
Yes, sir, you are audible, sir.
Okay, okay. So session is recording already done, na? Or
Yes,
we
yes,
are recording another
Yes, I am
lecture?
also recording.
Okay, thank you. Okay, ma'am, you can start now. Thank you.
So good evening, everyone. My lecture is about the soil improvement using stone columns. It's the techniques and the benefits. So the first thing is, what is problematic soil? Some natural soils, they do not have enough strength, stiffness, or stability to support buildings or structures safely. And these types of soil often settle too much. They don't drain water properly, have low resistance to force, or they can be easily compressed. So because of these problems, we cannot build directly on them unless we first improve the ground. And these soils are called as the problematic soils. Let us talk about some of the problematic soils, like if you will see the soft clay. What are the problems here with it? It is very weak, it holds water, it settles slowly and can't support buildings well. That's right. Silt becomes weak and slippery when wet, and it doesn't drain water properly. Expensive clay like black cotton soil swells when wet and shrinks when dry. So these movements can crack the buildings. Collapsible soils look strong when dry, but again, they suddenly sink when they get wet. Marine clay is very soft and takes a long time to settle with poor drainage. Dispersive soils break apart easily in water due to salts, causing erosion and washout. So these types of soils all need improvement before any construction can happen safely. So for different types of the problems, we are having different ground improvement techniques. Okay, so if you will see, here I am going to concentrate on the stone columns. So focusing on the stone columns, these are generally used for soft clay, stiff clay, silt and silty sand. They help in improving the bearing capacity, reduce the settlement, and also they allow the drainage. So, but if our soil is very soft or just like a peat or soft clay, then stone columns may not be enough. Then we need to strengthen the stone columns also. In that case, we can go for the encased stone columns, and generally geotextiles, they can be used for encasing the stone columns. So again, geosynthetics, when they are used for encasing, they make even the weaker soils able to get stabilized through the stone columns by improving the confinement and the load transfer. What are the stone columns? So some brief introduction was given by Professor Cole also in the previous lecture about. So these are widely used for ground improvement techniques. So stone columns are the vertical columns made of compacted stone particles installed in weak or loose soil to improve its performance. So they strengthen the ground and they do not act as foundation itself. So this is the difference between, if you say, what is the difference between the piles and the stone columns? So stone columns are not the foundation itself. So these are not shallow foundations, these are not deep foundation. It's purely a soil improvement technique. Okay, so here the process involves replacement of the weak native soil with a densified column of aggregate, which provides more strength and stiffness. And the improvement in soil strength comes mainly from the stiffness of the stone column, which helps in distributing the loads and reducing the settlement. So here on the right hand side, you can see the illustration showing the construction process and a real life site where stone columns are being installed. What are the merits or advantages of stone columns? First thing is they offer rapid installation. These are very cost effective. That's why these are popular choice in many construction projects. Secondly, they improve the load bearing capacity of weak soils and effectively reduce settlement, which is crucial for supporting the structure safety. Again, they are versatile. They are suitable for stabilizing various types of the soils like soft clay, silts, loose sands. They cause minimal disturbance to the ground and they are considered environmentally friendly compared to more invasive methods. And further, by encasing the stone columns, we can further enhance their strength, their confinement, and their overall performance. So, again, you can see the various, on the right hand side, you can see the various soil improvement techniques. But again, we can say that these stone columns, they stand out for their simplicity, efficiency, and adaptability. So, types of the stone columns. So, depending upon how they are resting. So end-bearing stone columns, if you will see, they extend through weak soil into the firm stratum or bedrock and transfer the loads directly to the stable layer. And generally, these are constructed by driving columns until reaching firm strata, ensuring stability for heavy structures. But floating stone columns, they are generally embedded within the weak soil without reaching the firm layers, relying on surrounding soil shear strength. And again, commonly used for lightweight structures, roadways, and embankments where deep foundations are uneconomically. So you can see both types. One is reaching up to the hard strata and other is just floating in the soil. And there are different installation methods of the stone columns. Displacement method, non-displacement method, and a vibro replacement method. So generally how the soil moves when we are going to install the stone columns. If it is just displaced, then it is the displacement method. If we are not displacing it, we are taking it out, then it is a non-displacement method, and then the vibro replacement method is there. With the help of the vibro float probe, we create the hole which densifies the adjoining surface and soil, and then stone filling is done with the help of the vibrations. So now I will focus on the basic design parameters of a stone column. So installation of stone columns in soft cohesive soil is actually the self-compensating process. Self-compensating process means softer the soil, bigger is the diameter of the stone column form. Now, due to the lateral displacement of the stones during vibrations or ramming, the completed diameter of hole is always greater than the initial diameter of the probe, because softer soil, there more displacement can be there. So diameter is always more. And how much more? That again depends upon the undrained shear strength, stone size, characteristic of the vibratic probe or rammer used, and the construction method. Second thing comes the pattern, how these stone columns, they should be arranged. Now, stone columns should be installed preferably in an equilateral triangle pattern. The first figure you can see here, the spacing S you can see, and this pattern is known as a equilateral triangular pattern, which gives the most dense packing. Otherwise, we can use the square pattern also. So typical layout is an equilateral triangle pattern. So here you can see both the types of the patterns, and you can note down how the spacing S is there in both the patterns. Then spacing, if we talk of the spacing, the design of the stone columns should be site specific, and no precise guidelines can be given on the maximum and minimum column spacing. But broadly, you can say that the column spacing may be from 2 to 3, depending upon the site conditions, loading patterns, column factors, and installation techniques, etc. These all things need to be taken into account while deciding the spacing. When we will design any single column, we will use one term, which is equivalent diameter. So the equivalent diameter, if you will see, again, here you can see what is equivalent. So the tributary area of the soil surrounding each stone column forms regular hexagon around the column. It can be seen in the first figure when the triangular arrangement is there. So this hexagon, it can be closely approximated. Yes. So it can be approximated by an equivalent circular area having the same total area. So then the diameter of that circle is known as the effective diameter, DE, and it is generally 1.05 times the spacing for equilateral triangle pattern and 1.13 times the spacing for a square pattern. Next term that is used is the replacement ratio. And again, to quantify the amount of soil replaced by the stones, we use the term replacement ratio. So generally it is, you can say AS upon A, means area of the stone column upon the total area within the unit cell. Now this total total area of the unit cell is what? Area of the stone column plus the area of the ground which is surrounding the column. So that ratio is the replacement ratio. So we can go to the next term, which is the stress concentration factor. So it is given by small n. Again, stress concentration occurs on the stone column because it is considerably stiffer than the surrounding soil. So from the equilibrium considerations, we can find out the stiffer stone columns should be giving us the greater stress in the surrounding soil and so on. So when we say that if we are having the externally applied load sigma, okay, then we can also consider the in the soil, if we consider the stress, that is sigma g. Then in stress taken by the stone column to the stress taken by the surrounding ground, that ratio is n. And generally this value lies between 2.5 and 5 at the ground surface. Failure mechanism. Single stone column, if you will consider, then if it is loaded over its area, then how it fails, that failure mechanism will depend upon the length of the columns. For columns having length greater than its critical length, and what is that critical length? That is about 4 times the column diameter. Okay, then whether it is an end bearing or it is a floating, it will always fail by bulging. Okay, long column, or you can just say that long column, whether it's end bearing or floating, it will always fail by bulging. But the column which is shorter than the critical length, that generally fails in general shear. Again, if it is end bearing, then general shear will be there. But if it is a floating column, then it will fail by end bearing. Okay. So when we have to design the stone columns, and we have to keep in mind some general points. So the first thing is how we calculate the lateral confining stress. So here we always assume a triaxial state of stress. That stone column is there and then the surrounding soil is also there. So at the failure, the triaxial state of stress due to the stone column and the surrounding soil, it is considered. And if sigma 1 is the ultimate vertical stress which stone column can take, then we can use this equation where you can say that phi s, that is the angle of internal friction of the stone column. Okay, and sigma 1 by sigma 3 is the coefficient of passive earth pressure, TP, of the stone column. Again, here we are assuming a plane strain loading condition. Second thing is, what is the ultimate load capacity and the settlement? We have to approximately estimate the ultimate load carrying capacity on the basis of the soil investigation data or by the test loading. Okay, so preferably we determine the initial load test on the test column installed, especially for the purpose of calculating the ultimate load. So we will install one stone column for testing prior to installing the all columns. Then comes the environmental factor. Again, environmental factor like if some aggressive environment is there or some agent like that is there, what is the condition of the groundwater there, what are the chemicals in the subsoil, all those factors, they are taken into account. Next point is load test result. Again, the settlement of the stone column at safe working load from load test results on a single column. We should never forecast it, okay, from the settlement of the structure. Yeah, sometimes it may be there that familiar foundations or familiar structure is there in that area, then you can take the fair estimate. But otherwise, the average settlement may be assessed on the basis of the subsoil data and loading details of the structure. Factor of safety. We have to consider some points for considering the factor of safety. For example, how reliable is the value of ultimate load carrying capacity of the column? You know, what is the type of the superstructure and what is the type of loading? What is the allowable total differential settlement of the structure? What is the manner of load transfer from stone columns to the soil? So we have to keep all these points in mind while deciding what will be the factor of safety. And generally, the minimum factor of safety for such a load test is 2.5 as per IS 15284 Part 1, 2003. So this code is actually used for the designing of the stone columns, or you can say how to use the stone column for improving the soil or stabilizing the soil. Again, we have to always apply some field controls. So when we have to, especially when we are going to use the vibro floats, we have to keep in mind the penetration depth, including the depth of embedment in the first strata, monitoring of volume of backfill added to obtain an indication of the densities achieved, and monitoring of the ammeter or hydraulic pressure gauge readings to verify the maximum possible density that has been achieved in case of the bifurcated columns. So minimum field controls by measuring or monitoring these parameters is always must. Field loading tests. Now, as I told earlier, irrespective of the method used to construct the stone columns, the initial load test should be performed at a trial test site to evaluate the load settlement behavior of the soil stone column system. So for initial load test, in order to simulate the field conditions of the compaction of the soil, minimum 7 columns for a single column test and 12 columns for 3 column group test may be constructed for triangular pattern. So here you can see for the single column test, we place these columns in this arrangement. Okay, so the spacing you can see as per the code, and what is the diameter of the stone columns as per the code for field loading test. Again, here in this figure, you can see that if we have to test the 3 columns in a group for the group test, then minimum 3 columns should be tested and minimum 12 columns, they should be arranged like this. Then we perform the test to carry out how to check their load and settlement behavior. So here again, the initial and final soil conditions at the trial site should be investigating by drilling at least 1 borehole, and 1 static cone test or the pressure meter test or the dynamic cone test should be done to assess the properties of the soil. After that, a granular blanket of medium to coarse and having thickness not less than 300 mm should be laid over the test columns. Okay, first of all, the test columns, they are prepared, and over that we have to put a blanket of the coarse sand. The thickness should not be less than 300 mm. Okay, and over that blanket, then we have to provide the properly designed footing. Okay. So again, we have to keep in mind everything. What would be the high water table conditions that will exist at the site, everything. And then we will start the procedure of applying the load. So if you will see the elevation, then it will be like this. Okay, so that was the plan. Now here you can see the elevation for the test condition. Now the load has to be applied to the footing by suitable sledge. Okay, so no impact should be there, no fluctuation should be there, and no eccentricity should be there. And minimum 1.3 times the maximum test load, we have to provide the load over the Kent ledge. And then again, load settlement observations, they will be taken up to the 1.5 times the design load, and settlement will be recorded by 4 dial gauges. Okay, and sensitivity of each dial gauge, it should not be less than 0.02 mm. And we have to keep these dial gauges diametrically opposite ends of the footing. So 2, these are visible to us, and 2 are perpendicular to this. Okay, so 4 dial gauge we will be taking, and we will take their average. Again, we have to apply the load in 5 stages. So in each stage, we will apply 1/5 of the design load, and it should be maintained till the rate of settlement is less than 0.05 millimeter per hour. And after that instant, next stage of the loading should be applied. Again, the design as well as the maximum test load, that has to be maintained for the period of 12 hours after stabilization of settlement to the rate. Load settlement and time settlement relationships, they can be plotted from the settlements observed for each increment of the load. For example, we can take the reading at 1 minute, 2 minutes, 4 minutes, 8 minutes, 16 minutes, half hour, 1 hour, 1.5 hour, 2 hour, 3 hour, 4, and like that. Okay, and these intervals that may be modified if you desire. And after taking at each time and each load, you can note down the settlement, and then we can plot the graphs. So after doing the or increasing it in at least 5 stages, then we have to load test. It is continued for 10 to 12 mm settlement at design load for the single column test, and 25 to 30 mm settlement at the design load. Okay, for a 3 column group test. Now, for example, we have to do the routine load test. There are few job columns, they may be tested only up to the 1.1 times the design load intensity, and minimum Kent of 1.3 times the design load. Okay. So one of my PhD candidate, Parvez, he's doing work on the stone columns. So he has developed a small model for testing the stone columns. So here, that is a test arrangement. A tank has been constructed in our lab. And here he has filled it with the kaolinite clay, and then you can see the arrangement. The hydraulic jack has been used to apply the load, and the settlement is taken with the help of the dial gauges. So this is the total arrangement where he's plotting these load settlement curve for the test tank. So this test arrangement has been made in our geotech engineering lab. So he's working on this. Okay. So after we can plot the settlement and pressure, then we can record the all the data. Now, here is the work done by a few researchers. If you can see, they have plotted the pressure and settlement curve for different types of the column. So here you can see the stress strain curve, settlement pressure curve for unimproved soil also. For you can see the ordinary stone column OSC, if you will see, and ESC is the encased stone column for different types, for the same surrounding soil, for the same material of the stone columns. Okay, so but how the encasing of the columns that affects, so that effect is clear in this graph. So firstly, what is happening there? That encasement is providing additional lateral confinement to the stone column, and this improves its strength. It helps it resist deformation, especially under the high loads. When high load is there, or the soil is very weak in both the cases. Okay. Secondly, the encasing material, it helps to prevent the loss of the stone particles. Otherwise, when the loading is there and the surrounding soil is very weak, then what will happen under the load? That stones, they will be displaced into that soft soil, so it will lose its shape, and when it gets damaged, it is not vertical, then it is not going to transfer the load, or it is not going to give the proper stiffness, because how much improvement is there, that will depend upon the relative stiffness. So that's why, secondly, we can say that encasing material helps to prevent the loss of the stone particles into the surrounding soft soil. And but it is important when the soil is loose or saturated soil, where there is more loss, okay, due to the quick reduction in the strength. And third thing is, encased stone columns, they improve the drainage characteristics of the system. The geosynthetic, they allow water to seep out, reducing the pore water pressure and improving the soil's overall behavior during loading. And next, you can say that encasement, it significantly reduces the settlement, and at the same time, it increases the bearing capacity of the treated ground. So here you can clearly see in this graph on the left, ESC line, triangle markers, that shows much less settlement compared to both the ordinary stone columns and the unimproved soil. Again, in the graph on the right hand side, you can see the vertical stress versus settlement. The encased floating stone columns, again circular markers, so they perform much better than both the non-encased columns and natural soil, offering higher stress resistance at lower settlements. So these benefits, they all contribute to important outcome. Which is that important outcome? Increased embankment stability. So with stronger support and better load distribution, the risk of failure due to foundation instability is greatly reduced. Again, so it highlights the importance of the encasement, that it does not only improve the strength and drainage, but it also ensures long-term performance and reliability of the ground improvement system. Then if we are saying that the encasing the columns, that is going to improve the stiffness. But then what is the effect of the encasing material? So that has been also studied by various researchers. So here, this slide you can see, it highlights how the stiffness of the encasing material that affects the performance of the encased stone columns. First, look at the graph on the left. So this shows the relationship between applied stress and footing settlement. The unreinforced soil, it shows the least performance with low stress resistance and high settlement. And as we move from ESC1 to ESC3, we see that increasing the stiffness of the encasement significantly improves the load bearing capacity. So here ESC3, it is with the stiffest material, it can resist much higher stress with much less settlement. So this clearly shows that higher encasement stiffness leads to better load transfer and improved stability. Now turning to the graph on the right. So this plot shows settlement versus applied pressure for different encasement stiffness levels in floating stone columns. So the pink curve, it is for ordinary stone columns and they settle more under pressure. And as the stiffness of the encasement increases from 1000 to 10,000 kilonewton per meter, curves shift to the right, indicating lower settlement under the same pressure. So this means that as we increase the stiffness of the geosynthetic material, the column becomes more effective at resisting pressure and minimizing the settlements. So key takeaway from both the graphs is simple. Stiffer the encasement, the better the performance in terms of both bearing capacity and settlement control. So again, you can see the type of the stiffness of encasing material, how it informs. Here you can see with the woven types of the geotextiles, which perform the best, showing the least settlement under increasing pressure. But ESC with non-woven geotextile, the triangles, though perform slightly less effectively, but still much better than unreinforced clay and ordinary stone columns. And the clay layer without any column, it shows the highest settlement, indicating poor performance. So here, the second trial of AC with non-woven geotextile, it confirms the consistency in its field. So this confirms that woven materials which are stiffer provide better lateral confinement, reduce and increasing resistance. So moving to the graph on the right, here you can see the bearing capacity ratio and the axial stiffness of the encasing material that has been plotted. So as the EA increases, the BCR improves steadily, going from 2.63 to 3.68. This means that stiffer encasing materials, they allow the stone column to support a higher load with less settlement. So again, the key takeaway is stiffer encasement, better confinement, it gives higher bearing capacity and lower settlement. So choosing the right encasing material, it can significantly improve the overall ground performance. Now, the different researchers, they have worked over the different lengths of the encasing. They have not encased the full length in every case. So from here, starting from with the graph on the left, you will see how load versus settlement varies for different configurations. Okay. If a plain clay bed has been used, okay, then the highest settlement under load is there, it is performing the worst. But when we add stone columns, either with stone aggregate, slag, or the combination, we see performance improve, but settlement still remains significant. However, as we introduce geosynthetic encasement and start increasing the encasement length, the performance drastically improves. Okay, if the encasement length is increased from D to 4D, the settlement progressively reduces under the same load, clearly showing that longer encasement lengths offer better confinement and better load distribution. So see on the images on the right. Okay, so these physical models, they show how bulging occurs in the stone columns as the encasement length increases. The first few images, they show visible bulging in the middle of the column when encasement is limited. Okay, but as we increase the encasement to 3D and 4D, the bulging is almost eliminated, showing much better stability and integrity of the stone column. Now, stone columns, they can, earlier, they were all, only and only constructed with the help of the natural aggregates. But just as the sustainability requirements are increasing, the use of waste material is increasing. So it is here in case of stone columns also. The stone columns nowadays, they are using the waste materials also. Okay. So if you will see, we are using the different type of the waste materials, and we are having some main waste materials which are used in the stone columns, like the tires, construction waste, silica, manganese, slag, okay, plastic, overburnt bricks, glass, steel slag. So lot of material that is being used nowadays. So this material again, it is used as a, it is generally used as a aggregate. So we have to first of all transform these materials in the aggregate form, and then we have to use this material. Okay, so here you can see what is the size range for the different of the material, and the different studies have been done on these materials. So we can compare the different waste materials also, how they have been used. Again, when we have to compare the various waste, we use efficiency. And we call efficiency as the ratio of load carrying capacity with any mix like waste to the load carrying capacity of using natural aggregates only. So this graph here shows only the best results obtained by various waste. So from the different studies where we got the maximum load carrying capacity, we used that percentage of that waste, that this particular waste at this percent, it gives us the maximum density, maximum load carrying capacity. Okay, so here you can see that 20% tires with 80% of natural aggregates, and replacement of fine, medium and large size tire by 20%, 25% waste concrete, 100% waste concrete, and 100% silica manganese slag. These are more effective, and 20% tire with 20% natural aggregates, that is the best result. So different waste, this is the summary of the literature view of the different wastes used as a material in a stone column. So then we come to the conclusion. So you can see that stone columns, they improve the strength, they reduce the settlement, and they are cost effective. Okay. And we have already discussed a lot of benefits. So again, if we want to improve the load bearing capacity, or if we want to use it for softer soils, then we can go for the encasement. And generally the geosynthetics come here. Okay, so they significantly enhance the performance by confining the stone columns and allowing it to carry more load. And optimal encasement length is around 50 to 60% of the column height. And last is the waste materials. They again, if you are going to use the waste materials alone, they are going to provide the lower bearing capacity than the natural aggregates. But if we are going to use them by blending them with the natural aggregates, then obviously we are going to achieve the higher capacity than the natural aggregates, or at least equivalent to the natural aggregates. Okay, so this is the one part. Then we can move to the second part. So here we said that we have to use the stone columns. Okay, whenever we have to use the stone columns, we cannot take their value arbitrarily from other project or from the previous assignments. We need to estimate the load carrying capacity of a column. So how we have to do it, we will now go to that slide. Okay. So when we have to design a stone column, especially in the cohesive soils, then the load carrying capacity of that treated ground, it is obtained by summing up these three things. What are the three contributions to that? Contribution of, first is the capacity of the stone column resulting from the resistance offered by the surrounding soil against its lateral deformation. Okay, stone column. Second is what? Capacity of stone column resulting from increase in resistance offered by surrounding soils due to surcharge over it. And third is the bearing support provided by the intervening soil between the columns. So again, the code IS 15284 part 1 2003, it is used to estimate the load carrying capacity of the column. So here you can see that the first thing is A part. Okay, A, B, C, three components are there. First, we will calculate or estimate the component 1, which is the capacity based upon the bulging of the columns. So again, here we have to consider the foundation soil is at failure when stressed horizontally due to bulging of the stone columns, and the limiting axial stress in the column is given by then sigma V is equal to sigma R K sigma P column. Okay, so again, limiting radial stress we have to consider, limiting axial stress we have to consider, undisturbed, undrained shear strength of the clay we have to consider, initial effective radial stress, and then final, okay, effective stress and effective angle of friction of the soil. That all these factors come into account for calculating the capacity based on the bulging of the column. So second is the surcharge effect that we are going to take into account. Okay, so again, if you will see initially, this surcharge load is supported entirely by the rigid column. So as the column dilates, then some of the load is shared by the intervening soil depending upon the relative rigidity of the column and the soil, and consolidation of soil under this load results in an increase in its strength, which provides additional radial resistance against bulging. So again, if you consider the surcharge load, what is it? The load of the sand blanket or the sand pad. And if the thickness of these elements is not known, then the limiting thickness of the surcharge loading, we have to represent it with the safe bearing capacity of the soil. and the increase in the capacity of the column due to surcharge, then it can be computed in terms of the radial stress. So here, that's why delta sigma RO is here, increase in mean radial stress due to surcharge. Again, it will depend upon the safe bearing pressure of the soil with the factor of safety 2.5. As per the code, we have to take the minimum value of the factors of safety as the 2.5. Okay, so again, this value, it will depend upon CU and NC. So when we have to calculate Q2, then we have to take factor of safety of 2 and then increase in the load of the column. Q2 is what? The increase in the safe load of the column, that is given by this expression. So here the surcharge effect is again minimum at the edges, and it has to be compensated by installing additional columns in the periphery region of the facility. So that's why when I showed you the arrangement for the test, then I showed you that for single column, we have to apply at least 3 columns on the periphery, and for 3 test arrangement, we have to use at least 12 columns. Then only we can test the group of 3 piles. So we need additional columns on the sides to find out the bearing support. And then third thing is bearing support provided by the intervening soil. So again, this component, it consists of the intrinsic capacity of the virgin soil to support a vertical load, which is generally computed by the effective area of the stone column, including the intervening soil for triangular pattern, that is taken as 0.866 S square, and area of intervening soil for each column AG, it is given by 0.866 S square minus pi D square by 4, and safe load then taken by the intervening soil Q3, that is Q safe into AG. Overall safe load on each column and its tributary soil is total Q. Q is the sum of Q1, Q2 and Q3. When we have to make the stone columns in the mixed soil, then we have to again calculate both the C and phi, and this capacity, it is generally estimated by the Bell's formula for passive pressure, and then we will use that. And the surcharge effect and bearing support of intervening soil, again, they have to be obtained like Q2 and Q3, just like in the same soil, and in the mixed soil, the only difference will come that when we have to calculate the we have to use the capacity, or we have to calculate, then we have to use the Bell's formula for the passive ratio. And when we have to use the column spacing, again, if you will see the plan area of the structure, then area per column is arrived at, that can be geometrically calculated, and effective spacing that can be calculated depending upon the pattern which we are going to use for the columns. If we are using the triangular pattern, then we will use it as 0.866 S square, and if it is a square pattern, then it is 1.0 S square. So again, design calculations, they are repeated till there is convergence of the assumed and the calculated column spacing. Then 1 or 2 trials may be required, and then only we can find out the spacing. And additional stone columns, they may be required inside and outside of the periphery of the loaded area, considering the pressure distribution and presence or absence of the surcharge, and permissible or expected settlement of the structure. And these additional columns may be provided either as rings or at a closer spacing for an appropriate distance inside as well as outside of the periphery of the loaded area. So again, so you can use this code and its various annexes for saying the settlement analysis. We want to do it by reduced stress method, and installation techniques of stone columns that can be also read in detail by using the IS 15284 part 1. Which is the design and construction for ground improvement guidelines for stone columns is the part 1. So I think that's all about the stone columns, ground improvement by the stone columns. So any questions? No questions. I think everybody has slept. It's too late already, I think. Yes, Dr. Senthil, it's over now. So I think I should thank everyone for waking up until now. They will have a good sleep today. A long session after a long day, a hectic day, then a long session. So any questions?
No, ma'am. No question.
Thank you. Thank you.
Thank you.
Thanks everybody for patient hearing. Yeah. Okay. Good night.
Thanks, ma'am.
Yes, sir. Yes, sir.
Recording stopped.
Parvesh sir, you can exit.
Okay, sir. Should I also leave from here?